Welcome to the January 2025 meeting of the Mornington Peninsula Astronomical Society. So we haven't met since November. Shown on the front slide here are a couple of things that have actually happened in the last couple of months. The big aerospace company Lockheed Martin has been working on 20 metre high solar panels for infrastructure to support a lunar human base. And they're especially designed to be very high to get around the deep shadows that you get on the lunar surface, and also to try and get around the static electricity problem of moon dust sticking to it on the surface, because you can't very well easily go out there and hose it down to get rid of the dust. So they're thinking ahead here to human colonisation on the moon. The next one across at the top there, showing the NASA jet that has landed in Perth, and they're going to be monitoring the next Starship entry, which I think is probably only a few days away until they launch it and it comes back in. And they're interested as it comes back in to see how it dissipates the heat, and so consequently they've got special permission to fly with all their lights out. So internal and external to the aircraft. So basically they're flying like one of these black ops aircraft that is under the radar, but they had to get special permission for it, and they are still tracked, but the idea is to make the aircraft as dark as possible as it's flying. Down at the bottom left hand side, the NASA's Parker Solar Probe was picked up first by Tidbinbilla in Canberra, and that was the first confirmation that it had survived its close approach to the Sun. It got to within 6 million kilometres, which is about 4 diameters of the Sun away from the Sun, so it's pretty darn close into the Sun. At the time it was travelling at 692,000 kilometres an hour, which is the fastest thing that humans have ever created. So it holds the record for the fastest thing that has ever been man-made. How it survived is it's got a special carbon foam shield on the front of it, and even so, that shield got up to about just under 1500 degrees Celsius, so pretty hot. But the idea of that is to put the shield between the Sun and the sensitive bits of the spacecraft, and the sensitive bits of the spacecraft remained about room temperature, which is pretty good going. Up in the top right hand side there, you may not have heard about this one. This was launched from India. It's part of the European Space Agency's program, the Probe 3. It's a coronagraph, so in other words it's out there to try and create an artificial solar eclipse. And it's actually 2 spacecraft that are going to be positioned, or are being positioned, 150 metres apart to within about centimetre accuracy in orbit. And one of them just merely acts as an occulting disk, so it holds up like a big blank disk in front of the Sun. And the other spacecraft is just positioned perfectly that it effectively can observe the Sun's corona, because the disk of the other spacecraft is blocking out the Sun. And by using this technique, they can effectively have an artificial solar eclipse that goes for about 6 hours at a time. And that was the telemetry for that was via a dish in Western Australia as well. So pretty impressive that they can get that sort of accuracy, and I'm sure they'll work in improving even that 1 centimetre accuracy. And lastly, down the bottom right hand side of the screen is the extremely large telescope, the ELO, from the European Southern Observatory. This is the one that's in the Atacama Desert, I think, in South America. Has reached the halfway point of its build, so it's halfway to fruition. And that's a drone view of it shown there, with obviously they've not got the slit in place yet. To give you an idea, it's 22 stories high, so it's a very big dome. It's 87 metres across and weighs 6,000 tonnes, so very heavy as well. The mirror inside it, the mirror comes in pieces, and 798 individual mirror pieces, each of them a unique shape, so there's no duplication, interestingly, anywhere around the mirror. So you've got to get the right one in the right spot, otherwise it's no good. And the meter itself is 39 metres diameter, and to give you an idea of that, that's probably about twice the length of this room that you're in at the moment is the size of that mirror. And what you're seeing there is the mirror cells have gone into place for actually holding the mirror. You can probably, if you're really keen eyesight, see a person down on the right hand side in the shadow at the bottom of the picture there, just to give you an idea of how big this thing is. So very, very impressive. Welcome tonight. First of all, we'll welcome all the new members, and we've got quite a lot of new members to read out, which I'll try and do now. We've got Christoph and Monica Szymanski, Susan Kiernan, David Green and family, Maya Turchek, Tom Kazas, Tobias Hay, Emma and Steve Wright, Martina Poliskova and family, Derek and Ginny Goodlake, Connor Foster, Ben Gavin, Bradley Smirk and family, Hilary Green and Tomohiko Harada, Katrina McNamara, Dilpreet Singh and Jazreen Kaur, Cass Skilton and Josh Spokes, Arusha Chandrasena, Ingrid Magnuson, Susan Farkas and family, and Joseph Silly. So we have quite a lot of new people to the society, welcoming those. Are there any of those new members here tonight? No, none tonight. Okay, just as well, because our new member officer Nerida is working tonight. So otherwise, we'll be pointing to somewhere else. Yes, Fred.
Just before you put that walk, I was going to ask you about that Tid Billiard thing. What was it? What's the objective of that? What's its purpose? That was what I was going to ask.
Well, Tidbinbilla is one of NASA's large tracking stations as part of its deep space network. There's 3 of those located around the world, and it's radio telemetry, both uplink and downlink from the spacecraft. Right, so they use it for controlling the spacecraft. Okay, so that's the welcome. Events will go through past and coming month. Monthly photo challenge I'll then throw over to Chris for that and the Mount Buller public nights. Guido can't come tonight, unfortunately, but we'll have Sky for the month again with Chris has kindly put up his hand to do that. I'm not sure if he wears a big red S on the front of his shirt for taking that one on. Then Dave Rolfe will tell us all about his visit to Mauna Kea in Hawaii. Then Phil Holt is here talking about Aurora. He captured Aurora with his gear fairly recently, and I'm not sure if he's got that as slides or whether the actual thing is here itself. Then we'll look at some space debris removal technologies and the missions and science of that. Now, this talk was actually prior to them announcing that the International Space Station was going to be deorbited, but they do make reference to it during the talk anyway, and then we'll close towards the end. So recent events, we've had quite a bit since we last met here. There was a Working Bee members night at the Briars on the 23rd November. Then we had a committee meeting that basically was looking at the upcoming events. The 6th of December we had a public night here that was 100% clouded out. 7th of December we had the Christmas concert in here with the Southern Peninsula Concert Band. 10th of December we had Peninsula Health's, that's Frankston Hospital's Community Care Unit here. And we gave them the first of possibly many of these sort of viewing nights. 14th of December, Christmas dinner here, where a number of Life members were presented. We had 68 present there. Cosmology discussion group was the last one for the year. That was here on Saturday the 21st. Then we got into the public nights in great earnest in January. 3rd of January we had 2 public events going on at the same time. We were here at the Briars with 99 people and no clouds, so that was an excellent evening. And simultaneously, in a collaboration with the Astronomical Society of Victoria, we had 3 members, I think, went up to Mount Buller, which is quite a hike from here. They also had about the same number of public present and the same cloud for that. And all in all, a good 3rd of January. Then the next night, we also had public night here at the Briars. That one was completely different. The cloud was almost total. And the interesting thing on that evening is we saw anti-crepuscular rays, and I'll explain some more about that in a moment. Public night was a bit less, probably due to the cloud cover kept some people away, and about the same cloud cover as we had here. 10th of January, which is last Friday, we had Guido give the talk, and the cloud cover was really good as well, only about 5% coverage. Now, a little bit about crepuscular rays and anti-crepuscular rays, if you've never heard that term. If you look at the picture on the left, at the bottom left there, you see the sun peeking through the clouds just prior to sunset. And that's an example of crepuscular rays. I would say almost everyone here must have experienced that sort of sight in the sky, either to the rising sun over in the east or the setting sun over in the west. And that's the view from the ground. On the right-hand side there is the view from the International Space Station looking downwards on crepuscular rays. And you'll notice there that in this picture the sun is over on the left-hand side, so it's shining from left to right. And the crepuscular rays are those 3 dark shadows that you see of the cloud being projected out to the right. And you'll notice that they don't converge or diverge as you get this view from the ground. They are in fact parallel rays when you see from above. And that's the thing, what these rays are is you're seeing either low-lying cloud or high mountains cast their shadow at a very low angle across the sky. And then if there are sufficient particles in the sky to scatter that light to your eye, then you'll see a crepuscular ray. So crepusculum is the Latin word for twilight, and these things always occur at twilight, so either at dawn or around dusk. So that's what they are. And the opposite is anti-crepuscular rays, and these occur on the opposite side of the sky. And down in the bottom left there, you see an example from Colorado of anti-crepuscular rays over in the left. So this is at sunset, and you're looking in the opposite direction to where the sun is in the sky. They're sometimes called anti-solar rays, and if you were to actually draw a line through those rays down to where the vanishing point is, that would be exactly opposite in the sky from where the sun is on the other side of the sky, the other horizon. Now they are also parallel, the same as the crepuscular rays, and the reason that they fan out again is just purely a perspective thing. So many people here will know that when you see a meteor shower in the sky, for example, they appear to radiate from a point in the sky, but they also come in parallel as well. So it's just an illusion, a perspective illusion. In the case of anti-crepuscular rays, the sunlight has to scatter backwards to get to your eyes, whereas the crepuscular rays is a forward scatter to your eyes. And the backward scatter is harder, and so consequently anti-crepuscular rays are fainter than crepuscular rays. And in extremely rare cases, the two can occur together and you can see them joined up across the sky. And what they then appear like is giant great circles passing overhead. I've not seen a successful photograph of it. I saw one as a panorama, but it was really, really hard to pick up the anti-crepuscular rays in the image. So if ever you see the ordinary crepuscular rays in the sky, have a look at turn around and look in the exact opposite direction, see if you can see any anti-crepuscular rays. And if you see the two joined together, quickly try and take a panoramic photo with your phone. So over on the right-hand side there is what we got at the Briars. Phil Peters took this on his smartphone, and that was exactly 20 minutes prior to sunset. And I would say most likely the reason why it was prominent enough to see was because of maybe smoke in the air from the bushfires over Grampian Ways would be my guess as to why it was seen there and not normally seen. So that was at the 4th of January public night. So coming up soon, in the following month, this coming Friday night, we've got a public stargazing night here at the Briars. Got 90 booked for that, and as far as I know at this stage, Trevor is still talking. Then on Saturday, we've got a workers' bee and members barbecue here at the Briars. All members are welcome. Committee meeting by Zoom is next Wednesday. Cosmology Discovery Group is into February there on a Saturday afternoon. Then the next public night on the 7th of February will be given by Guido, and that's already booked out. Then on the 15th of February, we've got the trivia night here at the Briars with the Cranbourne Lions concert band. This has been going for a number of years now, and that'll be a 6 p.m. start. And is that having a barbecue, Dave? Do you know? Yeah, and that will also have a barbecue with it. And we've still got a little bit of headroom there, so if you're interested in coming along to that, it's usually well attended. You will need to book that online to come along. And then 19th of February, we have the MPAS meeting. And for those of you who haven't yet bought a calendar, that's still available out at the front desk for $20, I believe. And that has photos taken by members here of the Society through their own gear as well for each of the months. And I'm pretty sure we've sold out of the almanacs, the Astronomy 2025 almanacs now.
Welcome to Astro Mofo number 20. So Astro Mofo is our monthly photo challenge for members, and the last challenge that we had was space people, items and phenomena in space that represent people or characters. We did have a pretty special event on the 19th of December, and a couple of us gathered here and a few of us managed to capture it from home. It was an ISS lunar transit. So it was a space station crossing in front of the moon from where we are. And when this happened, it always happens in a narrow path, and it just so happened that the Briars here was pretty much almost a little bit off centre to that path, but we were still able to see it, or a couple of us maybe saw it skim the moon from here. This video here is captured by Sylvie Grandit. It's from her home, not from the Briars, using a sea star. So you can see that shadow crossing across the moon. That is actually the ISS. So I've slowed that down. This is at full speed. The next one is at half speed. And the next one is at 1/10 speed. So it does skim through the moon pretty quickly. It's over in the blink of an eye, really. So that's actually a bucket list item. So well done to Sylvie, and there was a couple of other members that managed to capture it. I missed it. But yeah, a couple of us actually did get it. And there is actually another couple coming up in the next week or so. So 19th of January, there's one where the path of it crosses right through Frankston, and that's a daytime transit, and that's happening at 5:30 a.m. If anyone's game enough to try it, and I might take my gear down to Frankston and try not to get it stolen. The other one is crossing through Aspendale at 10:23 on the 25th of the 1st. So a couple of more opportunities to get it. You can actually capture it during the day as well. So you do see a bright flash crossing the moon on those 2 days. On the 19th, the moon's going to be up at about 50 degrees elevation in the north. And on the 25th, it'll be up at 73 degrees. The higher up it is, it means that the space station is actually closer to us. The lower on the horizon, the station's actually further away. So if it's up at 73 degrees, it's passing almost directly overhead. So if we do capture it, you'd expect it to be quite a bit bigger than it would be if it was lower on the horizon. And one of the app that I use to find this is called ISS Transit Prediction Free, and it's an Android app. So I'm not sure if there's a similar one on available for Apple. Okay, this challenge was completed by Sylvie, whose capture we just saw, Chris Black, Russell Smith, David Rolfe, Greg Walton, Nick Axaris, Liam Laub, and myself. And this is a capture I got of the Gabriela Mistral Nebula, which is in Carina. It's actually just off the Eta Carina Nebula, just to the side of it. And it was so named because of its likeness to Nobel-winning poet Gabriela Mistral. So, you know, I didn't get it at first, but then I saw that photo and I thought, yeah, there's a bit of a similarity there. And this was through a 200mm Newtonian. Next we've got, this is also the ISS transit captured by Chris Black using an 8-inch Dobsonian. So no tracking, but just a Dobsonian. And the moon takes, I think about a minute to go across the field of view of the Dobsonian. So you can park it and let the moon slowly go across the eyepiece while you're capturing the frames. And you do need a pretty high frame rate on your camera to be able to capture it. Because if like you saw before, it's over in a flash, and if you don't have a high enough frame rate, you could only get maybe one or no frames of it.
Is that a photograph? Is that the camera, or is that the actual colour, the colouring that's on the moon? I was led to believe it was just grey and dark grey and nothing else. That looks like purple.
It depends on the colour balance when you're processing it, but I mean, whether the moon appears white or whether the moon appears grey depends on how bright it is.
So that is the moon itself.
That is the moon, yeah. That big round thing over there is the moon. No, well, no, it's not the field of view, but
at 7 o'clock.
Yep.
Right, where you got them 2 red marks, and it looks a different colour to everything else. So that's
the dark patch.
Just wondering whether it was just people taking a photograph.
You mean that dark patch? Yeah, that's one of the mare on the moon, one of the C's there. Close to where, I think that's pretty close to where 15 and 17 landed, and I've actually got something on that next. But yeah, so that is the moon, and the moon actually does have colour. So you can actually capture photos where you do bring out some of the colour in the moon, and the astronauts, when they were on the moon, when they did scratch the surface, it wasn't just white and grey, they did see coloured rock underneath the dust. Yes, John?
The only way I could find it on my shots was to compare it with the moon after a couple of minutes.
Right.
And then use it under a stereoscope. Flip from one, like a blink microscope.
Yep.
Only way I could find it.
Yeah, it is tiny. I mean, if you see how small it is, if you just sort of took a picture of the moon and it happened, that wouldn't, you might think that was a speck of dust or something, but if you're purposefully trying to capture and you see it streak across the moon, it's yeah, it's a pretty good capture.
In other words, if it's white.
Yeah, that's right. And that's with the problem with the daytime transfers, and I've seen a video of it, is it's a bright dot going across what's already a white moon. So it's already, you might be able to capture, I think what's happening is it is passing across part of the shaded part of the moon. So you might see the bright dot cross the shadow of the moon before it goes off into the sky again. But yeah, so it's not an easy one, but it is a bucket list. This was actually the field of view. I put my camera here on Big Blue, trying to catch it, and I was doing a bit of hand tracking, trying to keep it, but I didn't capture it. I think I must have been pointing in the wrong spot at the wrong time. And it is a pretty narrow field of view of the moon through Big Blue in the camera, but I didn't let it go to waste. There's 2 Apollo landing sites on this field of view. So these are technically, people were there, space people were there. This one here is Apollo 15 landing site, and the one up there is Apollo 17. So Apollo 15, we had David Scott and James Irwin landed on the 30th of July 1971 at Hadley Apennine, and Apollo 17 was the last Apollo mission, had Gene Cernan and Harrison Schmitt land at Taurus Litlow at those locations. So no space people in that photo, but they were there at one time. So next we've got this one by David Rolfe of the Gabriela Mistral Nebula, captured with a monochrome camera and LRGB and HR filters. So RGB, red, green and blue filters, and HA, hydrogen alpha. Hydrogen alpha because there's a lot of hydrogen in Eta Carina, and that really dominates, so you get a lot of detail from that. And Dave's done some pretty funky mixing with the colours to get this nice shot. And I'm always envious of Dave's stars because you're always getting them pinpoint. So you got to show me something on that. Okay, this one is Thor's helmet. So the god of thunder, and it's basically what it's caused by is there's a Wolf-Rayet star in the middle of that, which is a really massive star, which is throwing off chunks of its atmosphere into space. It's coming out to the end of its life cycle, and those layers from that Wolf-Rayet star interacting with interstellar gases, and as they do that, and the radiation from that star causes all this to glow in what we see as Thor's helmet, NGC 2359. And this was Again, with my 200mm Newtonian, it is a pretty small object, so seeing it through a short focal length refractor, it looks pretty tiny, but through about 1 metre focal length, and this is a little bit cropped as well, but it's quite a nice object to look at. Through it, you can't actually visually see it, but it's a nice one to photograph it. Now we get to Orion, Orion the Hunter, which is the dominant constellation in the sky at the moment, so pretty much everyone knows it. A lot of people know it as the saucepan and handle, but it's actually Orion's belt and sword over there. And this one was by Liam Laub with his Nikon D750. 195 frames Liam captured for this one, 30-second frames, and only at ISO 50, so low ISO, not a lot of light gathered, but a really low noise image. I helped him process this one to get this result, but the key features that we actually see in Orion, we've got the main stars Rigel and Safe up here, which are actually his feet. So when we look at Orion from the southern hemisphere, we actually see him doing a bit of a cartwheel. So he's upside down for us because we see his sword hanging up in the air and his head is down below. This is, oops, let's go back. That's his head over here. Then we've got Bellatrix over here and Betelgeuse over here are the four main stars which frame it. Then across the belt we've got Mintaka, Alnilam and Alnitak. Some of the key features that we find around these stars, we've got the Witch Head Nebula up here, which is actually not in the Orion constellation, but it's in Eridanus. The border of those, oops, I keep going that. The border of those constellations is just sort of runs through there somewhere. Around Betelgeuse, you'll notice this little dark bell-shaped ring called Pickett's Bell. We've got the open cluster here, what is it, NGC, well no, it's Colander 69, that forms Orion's head. There's also a little reflection nebula here, which I didn't know about, so we'll might have a crack at that with the Newtonian at some time as well. Now in the sword we've got the famous Orion Nebula, the Great Orion Nebula, M42, and just behind it there is where the Running Man Nebula is. And then around Alnitak is where we have the Flame and the Horsehead Nebulas just there. We've got Barnard's Loop, which is this red glowing gas of hydrogen around the belt and sword. M78, the little reflection nebula in there, is also known as Casper the Friendly Ghost by some. And to counteract that, on the other side of Barnard's Loop to Casper, we've got the Boogeyman, and that is that little dark nebula there. So these are all interesting targets for telescopes. This was also my capture of the same thing. I've got a slightly longer focal length. Liam's was 35, mine's 50mm, so it's a little bit more cropped in, but it's with my Astro camera and some longer exposures. So I managed to pick up a lot of the nebulosity, and you can make out the little Boogeyman Nebula down there a little bit better. My field of view missed out on Safe, which is up there. Yeah, it's a really, really great target for a wide field photo, and that was my capture of M42, the Great Orion Nebula and the Running Man, which was done with a couple of different filters and mixing the images together with an 80mm refractor. Now we've got these two images of the Running Man taken by Greg from here at the observatory using two different telescopes. So you can see that's the Running Man Nebula there. This one here is with a Newtonian, obviously, because you can see the star spikes from the spider in the Newtonian, and the other one, the really close-up one there, is with a 350mm Meade, and it really does pick up some really nice detail across the Running Man's head and in the clouds around there as well. So that's a really good comparison of what you see through the two different field of views of two different telescopes. And then we have Nick Axaris took this one of the Great Orion Nebula and the Running Man as well in a pretty complicated process using two different telescopes. So he used a longer focal length telescope to capture the central part of the nebula here and get all that lovely detail that he's got. And he used, which is a 130 aporefractor, which is a longer focal length, 657mm, and then he used a smaller focal length telescope, an FRA 300, to capture the area around it, which is all the dust, and combined those together to produce this beautiful image. And this one is by Russell Smith, which is obviously, as he says, a mandatory M42, just in natural colour, RGB, with a monochrome, oh no, that's with a colour camera, 2600 MC, and a similar focal length to the large telescope that Nick used. So that's a sort of field of view from the large telescope, and the smaller one get all the dust around it. Also a couple by Sylvie of Orion. So we've got his Alnitak over here, and she's managed to capture the flame and the horsehead with a few 30-second exposures with her 150mm refractor, and also M42 in Orion's sword as well. So some really nice photos there. The horsehead is actually not an easy one to capture. You've really got to get a bit of time on it, some longer exposures, because it is a pretty faint nebula. Okay, our next target will be the Vela constellation. This will run between now and our February meeting. So Vela forms the sail of the Argo Navis, the great ship, which is also formed by Carina, the hull, and Pupus, the poop deck. So the Vela, the sail of the Argo Navis, has got some really interesting objects in it, like the Vela supernova remnant and a couple of other nice hydrogen alpha emitting nebulas and that sort of thing. So it's really good for telescope, and it's also good for getting some wide field shots similar to what we got with Orion. It's also close to the Milky Way, so if you get a wide enough shot of the area and the constellation, you'll get a bit of a streak of the Milky Way through it as well. So send your photos to any of the socials, and I'll pick them up to include them in the next summary, or eScorpius, and just put the subject of Astromofo if you submit anything, or you can email it to me directly. And Vela, just so we see where Vela is actually situated. If we're looking, this is south, and the south celestial pole is up around about here. We've got Carina running through here, and Pupus and Carina through here, and Vela is just in there. So that's where it is. We've got the Southern Cross and the pointers just low on the horizon down here. So if you follow that line up, that's where you hit Vela. Okay, any questions?
Chris?
Yes.
Well, as you know, when I come up with a children's telescope, I just put my telescope on the moon or see black and white, and I'm not sort of like advanced as what you are. But when you see the colours of them photographs, is them colours actually in the sky, and what causes it? Is it the gases?
Yeah, the colours of the nebulas are there. Our eyes have a really hard time picking them up looking through a telescope, because they're so faint. Our eyes aren't sensitive enough to pick up the colour. Well, it's like looking at a picture in a dark room. You can see the picture, but you can't really make out the colours in the photo unless you turn the lights on. With respect to coming up with the different colours in the photos and the different colour palettes, that comes down to how you process and how you mix the colours, and what sort of camera you use and how you balance it all. So
There are definitely colours in the sky.
There are definitely colours there. So even if you just use a normal camera and take a normal photo of the Orion Nebula, it'll come up pretty much the way it came up on Sylvie's photo there, with the pinkish middle and then the grey and all the other colours.
So the other question, you probably Greg more about it, won't you? Mine's a 2 manual telescope, but I am thinking of changing over to a computer one, but he's told me to train on the ones we've already got, which is space common sense. Yep. But if I did have a computer one, would it be better in the sky, like picking up them colours as a mode, or wouldn't it make any difference? It wouldn't make a difference to how many colours you pick up. What I wanted to know. Yeah. Okay, mate.
All it does is it keeps you tracking, so that when you're taking a photo, your stars don't streak and you get a sharper image.
Just adding something to that, remember that the retina has 2 types of sensitive parts. namely cones and cylinders. Now, one is for colour, one is for black and white. The colour ones are nowhere near as sensitive as the black and white ones, so everything tends to come up in shades of grey. To get the colours, you've got to have just simply a brighter source.
Yeah, and you can use some certain filters on telescope eyepieces which help bring out the colours more, because they'll knock out some of the glow. And
I know of someone who bought a 29-inch to observe
yes.
to see colour, and apparently was successful.
Look, I have seen.
Probably nearly blinded himself in the face.
I have seen Ida Carina through I think it might have been around a 29-inch telescope, and yeah, you definitely see a bit of colour, but you need a lot of aperture, yeah, and a dark sky.
There's one other thing, Chris, when you put it on, they took the photograph with this Dobsonian 8-inch and all that. Is it any much different from a 12-inch telescope or an 8-inch in taking them? Is there much difference? Is it better with a bigger one? Or?
The bigger the better. Well, it varies, because the bigger your telescope, usually the longer your focal length, so the narrower your field of view. So it depends on what you actually want to capture. If you want to capture small things, galaxies or planetary nebulas or planets, a long focal length, big aperture telescope like the Meade that we have is ideal.
I know some people put little cameras over mine, watch it too far, that's fine. You know, I was just looking at Dobsonians and there and...
It's very much horses for courses, and like you saw in Nick's photo, he used two different telescopes, two different focal lengths for two different parts of the nebula. So a longer focal length telescope for the detail in the core of it, and then a shorter focal length with a wider view to capture all the gas around it. All good? All right, I'll hand over to Chris for... What do we want next? Sky for the month or Mount Buller? We'll go Mount Buller. Okay, so Mount Buller Starfest is a event held in Mount Buller, organised in conjunction with ASV and MPAS in conjunction with Mount Buller and Arlberg House. Arlberg House is one of the establishments there, a hotel and accommodation, and it was held on the 3rd and 4th of January this year. The January 25 event was the third one. They are held in summer and in winter, and the idea of the summer events is to promote people coming up to Mount Buller during the off-season and making use of the facilities there and enjoying some of the dark skies that the area has to offer. Okay, so what do we got? We've got? This is pretty much the view from the roof deck where we set up our telescopes, and this is a photo by Dave from up there. So we were up on the roof deck of Arlberg House, where there's the nice bar below and bistro, and then you go around and go up some stairs, and you end up on this roof deck here with which has got some pretty nice views. So the MPAS members that were in attendance were David, Jamie and Landon Rolfe, Nerida Langcake and her daughter Piper Grierson, me and my wife Nikki, and ASV members Mark Ascaro with his son and daughter helping him. John Michaels and Kate and Lee Green also brought equipment up there to show the public. Also,
sorry, was your station in that where the ski lifts are? Or?
Yeah. So you can see the ski lifts just they were just crossing right in front of us.
Went up there in the bloody summer once, and the wind nearly blew me bleeding head off.
Yeah, we had some really nice conditions where we were there. It was the first night. This is pretty much on the first night, so it was completely clear. We can see some crepuscular rays here actually as well coming up from behind the ski lift there, from the mountain behind. Now the volunteers that went, we were accommodated in the medical centre bunkhouse, which had some shared facilities, shared kitchen, and some nice and warm bunk rooms for sleeping in. And this is some of the equipment. So we've got over here, Dave Rolfe bought his bino viewers, which were always pretty popular. We had a couple of large Dobsonians, one of Nerida's, and the other one was Michael John Michael. Yeah. And that's, let's go back. My little 8-inch Dobsonian in the front. And then a refractor there, and then off to the side there was Kate and Lee had a astrophotography set up where they were showing some live views of the moon and that sort of thing to the people, and Mark was doing the same thing with an astrophotography setup. So there was a pretty good array of equipment on display that people were able to have a look through. We had around about over 90 people in attendance on the first night, which was pretty good. They were a pretty good crowd, very enthusiastic. It was a really good atmosphere with people, you know, having their kids there. They were able to purchase drinks downstairs and bring them up and just really take in the views through the telescopes. So it was, it was a really good atmosphere, really good night. So pretty much 100% clear on the first night. I think do we have actually a number on the attendance?
Yeah, it was about 100 the first night and 65.
Yeah.
Also Alex was up there. And
yeah, Alex Cherney and Diego.
they were doing an imaging
That's right. They were also doing an imaging workshop, which was separate to the. It was sort of combined, wasn't it? Yeah. Yeah. So yeah, the main objects that we had were obviously the planets, the moon. We had a really nice crescent moon, which oohed and ahed a lot of people. Venus, Saturn, Jupiter, and then a few other of the common objects that we look at. Mars made a very late appearance, so I don't think too many people got a look at it. The Saturday night though was about 65 people still turned up. It was very cloudy, and it was just sort of pretty much waiting for a gap to appear in the clouds to be able to point the scope at something. But we did get views of the planets through some thin cloud and the moon as well, so that pleased the people.
Were they members from other astronomical societies, or were they mixed?
There was, I think, someone came up from Gippsland, and I did also meet a couple of other members from ASV who lived around the area.
Did anybody?
I didn't notice anyone from anywhere there, but I did see there was a couple of ex-ASV members who turned up and were talking about renewing their membership, and you know, that people that hadn't come to volunteer, but they did still turn up for the viewing night as well. Okay, what else we got? Extracurricular activities. So when in the off time, when we're not looking through scopes, the Rolfe boys were given a lesson in throwing darts by my wife. What else have we got? There was a hike. There was a nice summit walk that we did on the first night, on the first evening when we got to Arlberg House. So you can take a nice little walk up the hill there. Pretty much from Arlberg House, there's a path that you just walk up and you go right all the way up to the summit, where you get some really nice views of the area. There's a little plaque up there which gives you some of the key features of the area and off in different directions that you can try and spot. Mansfield Zoo, it looks pretty interesting. We didn't go to the zoo, but Dave Venerida did with the kids, and saw a few of the animals there. Nikki and I hiked up to Craig's Hut in Mount Sterling. Well, we drove about 20 k's along a dirt track, shook the heck out of the Volkswagen, and then had to walk the rest of the way because it was a bit of a rough track the rest of the way. So. But it's yeah, a really nice area, and you can't go to Mount Sterling without seeing some horses. There was a few riders trekking up there as well. Craig's Hut is actually not a real hut. It's not an original hut. It was built specifically for the man from Snowy River. It got burnt down a couple of times and rebuilt. The first time by the local four-wheel drive club. They put some money into it because it's a local attraction. People go up there. You've got great views, and it's a really nice spot to sit and have lunch. And the second time it got burnt down, it was rebuilt by the local council with some government money as well. So they keep rebuilding it. I don't know. After all these rebuilds, they still haven't put in a kitchen and a toilet. So, and that was Mount Buller. So yeah, really great event. And if you get the chance to head up that way at any stage, even during the summer, it's a really good spot to do some viewing, do some photography, and yeah, worth the trek. Okay, Sky for the month for January, February 2025, prepared by Guido Tack and presented by myself. So the cover image, Guido always picks the cover image as being the photo that Nerida uses in her monthly article. And this one is of the Dolphin Head Nebula by member Nick Axaris. So a really lovely image there. Okay, solar system between the 15th and 15th of Jan and 15th of Feb. We've got the inner planets viewed here. So Earth, Venus, Mercury and Mars out on the outer. So Mars is almost at opposition, you can see from here. So it's the Sun here, Earth here, Mars directly behind. So it's pretty much the best time of year to be viewing Mars. And when we see from this, this diagram here is anything on the right side of the Sun is an evening object. Anything on the left side of the Sun is a morning object. So we see Mercury on the, looking at the screen on the left, it's a morning object and it's speeding around there pretty quickly. So 31st of Jan, it is almost at superior conjunction with the Sun. So it's directly on the opposite side of the Sun to where we are. So it'll disappear from view before it starts appearing again in our evening sky, but always a very difficult one to spot Mercury because it is always very close to the Sun, low on the horizon, usually lost in the twilight there. Okay, zooming out, we're looking at the larger planets here, and again, anything on the right side of the Sun is an evening object, anything on the left is a morning object. So you probably would have noticed previously the inner planets Mars and Venus, they're all on the right side of the Sun as well, as are Jupiter, Saturn, Uranus and Neptune. So pretty much all of the planets at the moment are all on the same side of the Sun and all visible in the evening sky. Okay, looking up at the full sky view, this is just before sunset, and as we can see, sun going down. We've got Venus, the Moon, and Venus, the Moon, and Saturn low on the western horizon at the moment. And then as we pan across the northern sky, we spot Jupiter, pretty much north, northwest, northeast in that sort of segment of the sky. And Mars coming up earlier and earlier in the evening in the northeast. So really hard to miss them because Jupiter and Mars are really bright at the moment, as is Venus. Saturn is pretty dim, a little bit harder to spot, and you've got to wait till it gets dark. The others can be seen pretty easily. So Uranus sets around midnight. Jupiter is now past opposition, so it's past the best viewing time, and we're speeding ahead of it. So it's getting a little bit further and further away from us, and appearing smaller week by week. So sunset is around about 8:30 at the moment, looking at the 1st of February. And like I said, Venus, very bright object, Saturn setting early, and Neptune sets early after sunset as well. Of these planets, Neptune is probably the only one that isn't naked eye. Uranus, if you've got really, really good eyesight at a dark site, you might be able to pick it out by eye, but they're really a bit more fitted for telescope viewing. Okay, 1st of February, night sky. I think this is an animation. Yep, here we go. So as the evening progresses on, we've got the main stars in the sky that we see at the moment. Okay, looking from the south, we've got the Pointers and the Southern Cross, pretty low in the sky, but as the month goes on, as the weeks go on, they appear higher and higher earlier in the evening. All the bright stars are pretty much up. We've got Rigel, Canopus, Sirius, Betelgeuse, where's that? Somewhere, there it is, Betelgeuse, Rigel, all of these really bright stars that we've got in the sky, some of pretty much the brightest stars are viewable from the southern hemisphere. Okay, looking at the major constellations, Orion is very much still the dominant constellation in the sky over here in the northern sky. Looking towards the south, like I said, Vela is just around about here with Crux and Centaurus still pretty low at the moment, but Vela appearing around about almost level with the south celestial pole at about 10 o'clock. So from an imaging perspective, as the night goes on, it just gets higher and higher, and it's in a great imaging position for getting photos of it throughout the course of the night. We've got Hydra streaking across the eastern sky over here, and Eridanus, the large snake, on that side over there. Okay, what are we doing now? Going further across the evening, we're getting Jupiter setting at around about 1 o'clock or 2 a.m, around about there. And then we're getting some of the minor planets, Vesta and Juno, rising in the east in the early morning. And there's Mercury poking its head up just before sunrise in the east. So that's around about the 1st, 2nd of February. That's how the sky is going to appear between now and the next members' meeting. Was it last night, the full moon, or tonight? We're very close to it, yeah. Well, here we go. 14th of January was the full moon. So that was last night. The new moon is happening on the 29th of January. So if anyone's planning on doing some astronomical viewing, the new moon is the best time to do it. Full moon again is on the 12th of February, and then the new moon at the end of February again, the 28th. Mercury superior conjunction, like I mentioned earlier, 9th of February, and the sun is rising at around about 6:30 a.m. At this time of year. Okay, the apparent sizes of the planets at the moment. So if you were to take a telescope with the same eyepiece and look at each one of the planets, this is what their comparative size would be at the moment. Jupiter's still the largest thing by far in the sky, but getting a bit smaller. Well, what's interesting to note is Jupiter and Venus are the two largest apparent objects at the moment. Venus is getting closer and closer to us. It's about to come, and it is entering more of a crescent phase. You'll notice over the next few weeks it'll become more and more of a crescent as it begins to pass between us and the sun. Then it'll have its conjunction, and then it'll start appearing in the morning after that. Mercury's still a little tiny and will be very difficult to see through the sun during its superior conjunction. Mars, best viewing time for Mars is at the moment, and we did have a few members looking at it a few weeks ago through the scopes here, being able to spot the ice cap as well. So really good viewing. Uranus and Neptune, two little blue dots, and Saturn you can still see its very edge on rings before it sets early in the evening as well. Okay, yes, now a lot of noise in the media about the planets aligning and parading across the sky. So all this stuff about all these photos that you see of planets aligned one over the other, it's not really like that. What you do see is that they are scattered across the sky. So from the west, after the sun sets, we've got Venus, very, very bright Venus, and a dimmer, paler yellow Saturn appearing. Neptune, you've probably got no hope of spotting it by eye, nor Uranus. But then as you scan across looking north, low in the northern sky, you'll spot Jupiter, and then Mars is rising a little later, and that is super bright at the moment, appearing as a really bright red dot in the sky. So around about 8:30 p.m. on 25th of February, they will all be lined up as so. Mercury makes an appearance as well. So Mercury will have come around from its conjunction and will be appearing in the evening sky as well, just after sunset. So we do actually have an opportunity on the 25th of Feb to view all of the planets. That's pretty cool. Okay, comets. It's 2024 G3 Atlas. So as we learned at the last photo challenge, C, it's an open orbit comet, very wide, very long period, maybe never to return again, designated by the C. It was discovered in 2024. G is January, February, A, B, C, D, E, F, G. So the letter is it, come on, help me out someone. April, first half of April, yes. And it was the third comet observed in the second half of April, discovered by the Atlas Observatory. So that's where the name of it comes from. Potentially visible after sunset from early February, or possibly possibly sooner, maybe within about a week or so. If you look towards the west after the sun has set, you may be able to spot it. It's just past perihelion on the 13th of January, so it's made its closest approach to the sun and survived, and magnitude -1 or brighter possible, so it could actually be quite a bright object. This animation shows its trek around the sun. So this is the comet here, as it's trekking around the sun, and I'll just get this playing in a sec. But this is where the sun is in the sky with its constellations, and Mercury there. That's a little bit there. But as time goes on here, so between the 15th and the 9th of Feb, the comet has come around past perihelion. It's starting to zoom out to the outer parts of the solar system again. And there we are. So Earth is here, Sun is here, comet is here, and as we said before, anything on that side of the sun is an evening object. On this side of the sun, it would have been a morning object, and so this is where we're seeing it fairly close to the sun as it makes its way back out to the outer solar system. Meteor showers, okay, we've got the Alpha Centaurids on between the 28th and the 28th of Jan and 21st of Feb. They peak on the 8th of Feb, which is only a few days before the full moon, so not the best time for a meteor shower to peak, but it is. They will be visible throughout that period as well. So bright yellow and blue fireballs, long-lasting trains, and like we said, they unfortunately peak close to the full moon. Sources, as always, are Stellarium software, NASA Eyes on the Solar System, Heavens Above, Astronomy 2025 by Wallace, Dawes and Northfield. Thank you very much.
Hello everyone, I hope you had a happy new year. We decided to spend December for a few weeks. We went over to Hawaii. I did a job over there several years ago on the main island and actually never went up to Mauna Kea, which was, how could you do that? I had multiple trips over there and never went there. So this time we decided to take the kids, probably for the last big family holiday before they move out of home. So we started off, we went over to the Big Island. So most people go into Hawaii, they go up to the, well, there's a laser pointer somewhere. Yep. Oh, okay. Oh, cool. Yep. For those that haven't been there, so most people fly into Honolulu up there on the, it's actually a smaller island, but that's where probably 90% of the population live. And we went down to Kona. I did a project down there, which is, Kona's around here somewhere. The project I did there was actually quite interesting and a good story of its own. So this company we used to work for is a Japanese company. They used to have an oil rig converted. They used to go out to sea at about 2,000, 3,000 metres of depth of water and bring up seawater from 2,000 metres below the surface. And at that depth, there's actually fresh water. So there's no salt that low. But it was very expensive having to fly people in and out of this rigs and then getting the product and piping it all the way back to mainland. So one of the only spots they could go to in the world was the large island where there's no continental shelf. So they core down through the volcanic rock, 2 kilometres, pop out the side, and capillary action actually brings the fresh water up to the surface. Virtually unlimited supply. Run it through some filters, put it in a bottle, put some Japanese writing on it, and charge about $10 a bottle of water. But it was an interesting project. I went there a few times. We set up the bottling plant and so on. So anyway, the whole time I did that, I never went to see Mauna Kea. So this time we're desperate to go over there and also check out the volcano. Mauna Kea itself, it's the tallest mountain in the world when you take it from the base. So yes, it's below the sea. It's actually taller than Everest. So that's the claim to fame. Now, I like Jeeps, so hired a Jeep, did some 4-wheel driving over there as well. after getting used to driving on the other side of the road. There's a few photos there of the rocky landscape, so it is obviously that island very full of rock. A little bit of topsoil on it, but generally if you dig down not far you're going to find yourself in volcanic rock. So you drive through the centre of the island, you drive up to Mauna Kea, halfway up to the climb you get up to 2,800 meters, that's not kilometres. That would be higher than in space at that height. The K shouldn't be there, alright guys, I did this very late at night. But anyway, so above sea level you go up to there. Sorry? Kilometres. And there's a visitor centre there. That's where you can normally go, that's as far as you can go typically, unless you've gone and organised a special Jeep. That took me a long time to find. So you actually find a hire company that will let you take the car past the visitor centre was a nightmare. 95% of them won't. So we found an off-road specialist there that would actually insure us to do that and allow the cars to get past. And there's a guy that checks there, you can sort of see there in that photo. He'll actually check your car to make sure it's in four-wheel drive and you know what you're doing before they actually allow you to proceed up the hill. Now at this point here, you've actually got 20% less oxygen in the air already, so you can already feel the effects of the altitude at that point here. So the visitor centre has got lots of those infographics around the wall there, a little bit of information about the telescopes up there. It's really quite small, but it's actually compulsory to stop there for half an hour before you go. The actual guy makes sure that you actually stop half an hour, acclimatise to that altitude before they'll actually let you go up. Even the tour buses have to stop for half an hour. It might also be something to do with the overpriced merchandise there as well. But
you got a pearl out, though.
I did. Everything's overpriced in Hawaii. Speaking of Hawaii, so you had a Hawaii, every restaurant you go to at the moment, when I was back there years ago, it was reasonably inexpensive for us. Now you go there, the actual prices on the restaurant are probably a little bit dearer even than what our prices here. So you go to we went to a lobster place there and it's like $70 a plate and you go, Struth, that's actually double that, what it's going to cost you Australian. So even McDonald's, the Big Mac check, so it was over about $10, $11 for a Big Mac equivalent. So Australian dollar was pretty poor, but anyway. So we started heading up the hill. It's actually very steep. You don't realise how steep it actually is. You can sort of feel your ears popping the whole way up there. There's about several different pullouts. Plenty of warnings they give you there. They give you a bit of a briefing saying that there's no medical services up there. There's no oxygen up there. No, some of the observatories actually have it for their own staff, but not for the general public. They actually try and discourage people from driving up there because obviously the ambos go up there when people collapse with the lack of oxygen. The terrain changes quite vastly from the bottom, and as you go up you go through all these different layers of light vegetation, rock colour, sort of a grey colour, and you go up a bit higher, everything turns red, almost like a Martian landscape. Heading up, there's patches of asphalt and patches of gravel. That's looking back down. We're well and truly above the clouds at this point, although there is a high layer of cloud, but the bulk of the cloud, because it was actually raining the day we went there, but it's raining at the visitor centre. So between the visitor centre and where we are now, you can see the layer of clouds. That's just a random dish down there. It wasn't really part of anything as far as I could tell. So we got up to the intersection at the top, and you can look out there and see lots of observatories, including the biggest one you notice there is the Keck one, which I've labelled in the next slide. James Clerk Maxwell, that's a sub-millimetre one, another array off to the side. The Subaru up there, that definitely needs another paint job. The Keck, well, that's very obvious with the 2 scopes, and the infrared telescope.
Is there any, Dave, is any, where you've just put there, is there any permanent staff up there?
Permanent what?
Permanent
Staff? I don't know. I think most of the astronomers are not up in the hill. They're down the bottom just feeding data. All of these, everything up there is all imaging, capturing, and fed down below. So there's certainly people working up there. I probably saw about 20 people in Keck. They had a little. I'll show you shortly. So that photo you saw in the last one was taken from point 2, where that public restroom is. And that was sort of looking back out towards the Keck and the Subaru telescope. That went back a slide. So that's where that shot was taken from. Sort of, laser there, somewhere there, looking that way.
So you have cargo with
Oh, it's a Jeep. They go anywhere. No, the car was fine, but you could certainly, by the time we got to that point, Leanne stayed behind. The people at the visitor centre talked Leanne into not going up the hill. She was panicking already at 20% of oxygen. She was already sort of feeling it. 40% less. So half again. So I was going to go, I didn't care. And I had Jamie who could drive me down anyway on his L's. Well, I wouldn't tell them that, but I was going. I said, Jamie, if anything happens to me, you got to drive back down. I'm going for it. And Leanne just said, no, I'll wait down here for you. See, she was getting bored down the bottom. So we got to the intersection at the top of the hill, and the first one we come to was the United Kingdom Infrared Telescope. Now, that is now morphed into the University of Hawaii Telescope, which was just behind it at one point. But they have a policy there. The older Hawaii Telescope, there's a plaque, which is the next one. I'll go back again. They're not, because it's a very environmentally sensitive area, cultural heritage as well. Once something's become redundant, they actually have to completely remove the observatory and put it all back to the way it sort of was. They can't leave old defunct stuff, because as technology advances, some of these telescopes and stuff just become obsolete. They become too small, taken over by space-based stuff, or just have no real purpose anymore. So the United Kingdom Infrared Telescope, they obviously ran out of funding, and they must have decided we'll just give it to the University of Hawaii because it's slightly better than their old one, and they don't have to worry about pulling it down. I'm unsure if it was actually being used. It didn't look very active. Then we got the old, one of the first ones that was built up there, I think in 1968, had that funny horn on the end of it. That was another University of Hawaii telescope. They must just take all the scopes when people are finished with them. There's about 4 of them up there managed by the university. The Gemini Observatory, an 8.1, there's a duplicate of that in Chile, I think. So they've got a north and a south version of that. That's there was people working in there at the time, so I think they're doing some upgrades. They weren't very talkative though. Canada-France telescope. They look fairly new. It was been certainly well maintained, probably better than most of the other ones up there, even though it was 1979, so they've obviously still doing it. They're actually looking at upgrading that, that's right. There's a plaque there saying they're looking to put an 11 metre. I think it has been approved, the guy was saying. So then we drove across the hill. You see the Keck out there on the, which just stands out. It's one of those panorama photos on the iPhone. It actually sort of had a dip, but I think that accentuates it. Off to the side there, the NASA Infrared Telescope, that was actually built to support the Voyager probe. So they were using that, I think, for to map where they were going to do planetary science. It's still used for planetary science. It's certainly got an old sign out the front that looks like it was from the 70s. Now the Keck was certainly the one I wanted to go and see, and that was the only one that actually had a visitor centre where you could actually go in and see the telescope. Everyone else's telescope were all locked up. They obviously just didn't care about tourism. The Keck there actually had a little room you could walk into with some information about it. It's not the greatest photo. It's you're down below it looking up in this glass room there on the right hand side. You can see you can't really see the optics. It's all just underneath it. The Subaru telescope. They were saying there was another thing we're reading there. Very cursed telescope. 4 people died during its construction, of all different reasons. It's also been damaged several times over the years. People working on it and dropping things and breaking part of the mirror. So they were saying that's a very cursed telescope. And I certainly need to coat a paint. Maybe nobody wants to paint it because it's just so cursed. Yeah, maybe. A bit of revenge. Then we've got the submillimeter array. There used to be another telescope just to the side there that was the original submillimeter array, but that was run by Caltech. You can't even see where it was. There was a picture there showing where it was. They've actually removed it. It was redundant, and they replaced it with that array, and that's controlled from in that control room there, which was part of the one behind it there is the James Clerk Maxwell telescope, 15 metre. It's a dish inside of it. I think I had a photo of it. Oh no, that was the Caltech one, sorry. It's a bigger version of that's what's in that other, the Maxwell one. That's what they decommissioned just last year, and you wouldn't even know it was there.
Is that radio?
Yes, that one's radio submillimeter. I don't know. Snow. Well, don't know the reason for that, but it is. Well, the other ones, I mean, that was decommissioned, and what's replaced it is that array out there. So maybe that's why they ripped it down. Wasn't a good idea. It is sort of a national park up there, so that was a sign as we're leaving. You can actually walk up to that summit, but you sort of sense if you lost your breath, you wouldn't get it back again. So one of the girls up there was a girl in an observatory up there. She was sitting at the door with an oxygen mask on, so she was obviously suffering, but so obviously they have stuff for their own staff. Chile's higher. Yeah, it's a lot higher, Chile. So yeah, it's just, I think the less air above you, the clearer the image. So that's essentially why it's up there. Heading back down through the clouds again.
Do they have a curfew on the times?
Yes, you have to be, you can get up there 1 hour before sunrise. That's when the tour buses turn up. They time it just there. And you have to be heading off 1 hour after sunset. Now, we went up there in the middle of the day. I were going to drive back and do a sunset trip, but I just basically lost interest. Done it once. They also check your car. It's got to be clean and all that. And by the time I did some more four-wheel driving, it was covered in mud and stuff. But they don't want to contaminate it with foreign.
30 metres also going to be put on Mauna Kea, is that still happening?
I don't think there's any new big ones being built up there. They're all going out in Chile. That one Peter was showing you before, I think that was Chile, wasn't it?
I thought they struck a deal where they were actually going to move something and put that up there, but there's no sign of anything happening.
No, there was no construction up there. A couple of other things while we were on the Big Island. Went out to a place called Green Sand, which is appropriately named. It's apparently the only beach in the world that the sand's green, and that's caused by some leaching of that special rock there. So that was pretty cool. And then we had a black sand beach. I think there's a few of them in the world, but that was really hard on the feet. That was really hard on the feet. There was lots of turtles there too, which you have to stay 5 metres away from, or the ranger there would give you a $5,000 fine. They're very specific on that. And then we went to the volcanoes over there. Now, we went to that big volcano in the Volcano National Park, and 5 days later it erupted. Couldn't have timed it. But we walked through this cave. It was a lava cave. I don't know if that cave would have filled up, but it was at nearly the same level and appeared on that plateau, which has erupted now, so you wouldn't want to be in that cave 5 days later. You can certainly see, I mean, I think it's always has some sort of smoke and fume to it, but I mean, 5 days later that's all lava.
Did they know that it was going to erupt in 5 days' time?
Sorry?
Did they know that it was going to erupt in 5 days' time?
I think it's always active. You can certainly see steam vents. No, it was unpredictable, so they simply shut that part of the park off when it is. And most people try and go in there at night and get the night shots. I did see a photo pretty much from this spot where I'm standing now, and yeah, that whole plateau was just a red glow to it. This would have been a week before Christmas. Yeah, about a week before Christmas. And that's it. And then, of course, we went to Pearl Harbor, which you have to do when you got kids that love military stuff.
So as the sign says there, my name's Phil. I've been a member here for 25 years. This is the first time I've actually addressed the entire assembly. What I'm going to talk about is my attempts to do photography of the entire night sky, horizon to horizon, using nothing more than a hubcap. We'll go to next one. So where the journey begins, when I was a teenager at school, supposed to be swatting in the school library, instead I was busy reading Sky and Telescope. Happened to pass across an article by a bloke called Chris Scher. He'd done some experiments with a Volkswagen hubcap and tri-X-pan film, for those of you who remember the film era, black and white film. Chris Scher actually recently had a photo on the spaceweather.com website of that sun-grazing comet taken from his place in broad daylight while it's in like 4-degree proximity to the sun. And he done that with some inventive work. Got his telescope to track the sun first with a filter on, then got it to reposition a few degrees away to where the comet was, then removed the filter, but had a really long baffle to stop any sunlight getting in the main, through the main lens of the telescope. So it was a pretty good effort. Everyone else is watching it on the web through the NASA satellites. He actually did it from home, so it was pretty good. So he's still pretty active. So there was a series of articles around that time, and this stuck in the back of my mind for many years and didn't really come back to me until about 1998. I started to get ready for the Leonids meteor storm that was going to hit somewhere around 99, 2000. So I thought I'd have a few practice runs. So this shot here was just with a standard 50mm lens. So the bit down the bottom left you can see part of Orion's belt and the sword, and they're trailing because it's about a 4-minute exposure, but there's a meteor shooting straight through. But the problem you notice is I've only got the last bit. Where's the rest of it? You know, it made me think I need more coverage, I need a wider angle, or I need more cameras. What would you need to do to get a better shot? And then thought back about the Hubcap article and thought, yeah, I need a convex mirror or something just so I can set up and get more sky. So the early experiments, first I needed to find the convex mirror, and was inspired by parking the car next to a truck one day at traffic lights and looking in his hubcap and seeing my reflection, the car in front and the car behind. I thought, that's decent coverage, I've got to get one of those hubcaps. No, I didn't steal it, I actually bought one. The shot on the right is sort of the first attempt. That first hubcap wasn't quite a spherical shape, it kind of flattened a little, so it distorted a bit too much. But the interesting thing about that shot in 2000 was that sky being all red, that's an aurora. I didn't notice on that night there was an aurora, so there's no, the right-hand side of that shot is the southern horizon. There's no real flare-up of an aurora there. So this is a very faint glow, but it's covering almost the entire sky. When I got those slides back from the development, weeks later, I then had to go and look on the NASA data archive for their NOAA satellite data of that particular date and like a KP index, as we call it today, exceeding 9 or something. So there was a major event on that night and we'd all missed it. But I just happened to have it. So it's a matter of, if you can have this thing operating often enough, there's a chance of catching some of these rare events. So with film, you can't really do much. You really need to get to the, when we get to the digital era and you have a camera with an intervalometer and do time lapse or multiple shots during the night, you can start to capture things. So going back to the original inspiration, which is trying to hunt down meteors, on the left, that was during a Geminid shower, so there's a long streak captured in the shot there. The northern skies towards the bottom in that one, there's a little bit of Orion popping through behind the camera tripod there. That shot was kind of ruined because the hubcap had dewed over by that time. So there's not much contrast in the image. I had to really sort of drag it up a bit just to be able to see that. On the right's a recent one, and you can see the meteor right down the bottom. That's almost the southern horizon, south or southwest, and just a tiny streak across there. These two meteors would have been incredibly bright events. It doesn't seem to capture fainter ones. Little flicks that you see in the night, it just doesn't capture them. So it really would only deal with the magnitude 1 or brighter type meteors. So it's kind of disappointing there that I get more area and I can see more sky, but I get less meteors almost. It's swings and roundabouts. You win in one direction, lose in another. So that's a work in progress, how I'll deal with that. The main boon of this thing is the aurora. So a couple of shots there. The one on the left is from May last year, that one that many of our members travelled all over looking for southerly aspects to get shots. We've seen plenty of members with time-lapse shots of that aurora. If you look at that the right-hand side in both those shots is the southern horizon. The one from May, you actually get a bit of a purpley glow extending even into the northern part of the sky. So many people who have a more standard kind of wide-angle lens would have been looking south. They would get much of that green and pink or red structure, but you actually lose. There's a lot else that's going on. This gives us an opportunity to find a way to capture some of that unusual event that's going on. I've got a time-lapse of this that I'll show in a minute as well. The one on the right is a recent one that sort of caught me by surprise. There was a coronal mass ejection event heading for Earth at that time in the Northern Hemisphere. That sort of calculated that they were getting it New Year's Eve. I just set the camera up and set it running, and the last shots were looking like that. It's quite a strong event. In terms of how much the extent is above the horizon. On the January shot, the tree that's to the bottom there, the western end, the top of that is almost 45 degrees above the horizon. So if you kind of track that around, the top of the red-pink area is above 45 degrees. We're getting to 50, 60 degrees above the horizon. So it's quite a large extent. And you can see it's almost going from the extreme east to west horizon. So again, having a fisheye effect and getting the whole structure is quite a valuable way to record it. So the time lapse from the May event. Some information there to orient you first, so south to the right. And you can see to the left this sort of pinky reddy glow, that the extent of it going into the northern sky. There are several of these patched together that happen sort of in hourly blocks, but that rippling red effect just keeps phasing in and out. I haven't yet checked what kind of timing we're looking at between intervals of that. There may be features to these events where collecting the whole thing and watching the whole thing progress and surge in and out may be clues to other behaviour or phenomena in the magnetosphere that create these timed events. Late in that particular aura, just before I finished up for the night, all we ended up with was a really bright green glow. There were no further sort of red eruptions on that. Incidentally, that corrugated iron you can see, that's the shed roof. I had to climb up onto the shed several times to set this up. Not a smart thing to do really, with a ladder and in a shed. So I've actually built a structure to get onto that shed in a safer manner, so the ladder has a surround, there's a platform, so there's no risk of falling off it. So I can do this more often. So this is the January event. Get that running. The top is the south in this one, and at the start there wasn't really much hint there was going to be an aurora, and it just sort of steadily grew. I'd gone to bed by now, but you can just start to see rays rippling across there, the green glow, and then it really goes off towards the end. Sort of about now, we get some more rays. So this was about 11:30 at night, our time, and it really erupted. And then, true to form, I'd only set it to run so many shots to miss the rest of it. But the other thing, in terms of orienting yourself here, you can see the northern part of the sky, you can see Orion down there and Jupiter. So one thing about this, because it's a mirror, everything's back to front. You could use some software and invert it so it gives you the impression of lying on your back looking up at the whole sky. I haven't done any processing with these. They're really just patched together and thrown together to make the movie.
You actually see the colour reflecting off the corrugated iron.
Yeah, and the tripod legs, you get that bit of pink glow on it. So that's, I think, about a 20-second exposure, 1600 ISO. So that's enough to get the reflection off the metal from the colour. So it's quite bright, the aurora.
What's the light pollution like there?
So where I'm situated, this is near Mornington Racecourse, onto the east of the racecourse. So south of me, there's no habitation till Balnarring or something. So I'm looking down the spine of the peninsula. But to my west, I've got Mornington, and at 3 in the morning, the racecourse lights come on, and it's just ablaze. So I have to do all my work before that time. To the east is fairly clear. You've just got a bit of the glow from the Lysarts at Hastings. So that's the advantage of being on that kind of green belt down the middle. So in terms of aurora photography, like a lot of people make a mad rush down to Flinders and whatever, actually you really just need to get into that zone that looks north-south. So you've got the south view and just set a camera rolling.
Do you level it, Phil? Like, how do you sit on top of your...
So that bit of timber across the top, so that's placed across the roof. Then the hubcap is stuck down on that, and that gets it to almost level, and the camera is on the tripod almost centrally above it. I'll go into some issues with focus and alignment later, but a very crude setup is all that's required, and take a few test shots and just adjust your focus to make sure you're getting close to pinpoint images. This is another crazy little film made on a public night here. So you'll see people coming up with the torches and having a look and whatever. So I was just explaining to people that you could do all sky photography with a hubcap. It doesn't have any scientific value, but it kind of gives you another impression of the event, where people are around you as you were if you were the camera. But you could sort of see a degree of slow drift of the positioning of the stars as they move across. So you've got about an hour's worth condensed into that period of time. Now, I'll actually pull out the hubcap, so I have brought it along, keeping it in a nice clean rag, because you want to look after the polished chrome surface, and you can see kind of the depth to it, that you're looking about a couple of inches depth. That affects your focus, because you've got a virtual image that's not flat. So you're photographing something that's got a bit of depth to it, and you're not focusing on infinity. So when you put this down on the tripod below the camera, what you need to focus on, there's a couple of inches of depth. So depth of field becomes an issue, and that's where, well, I've got it listed on there, lens speed. You might have a fast lens at f1.4. You'll still need to possibly stop it down to 2.4 just to get the depth of field, so you've got all of it in focus. Otherwise, you'll have the middle in focus and the edge not quite in focus. And so that shot of the meteor I had, where the meteor was right off at the edge, you might have that out of focus, but you'd focused on the middle. So you're trying to get the whole thing to focus. And the other factor at the top here, mounting distance and focal length. So if you have a longer focal length lens, you can mount your camera further away from the hubcap. That reduces the size of the image of the camera in your shot, so you obscure less of your background sky. So the advantage is to have a slightly longer focal length. Notice to get the lens speed, around 50mm lenses on 35mm SLRs are some of the faster lenses they ever make. So I've got an f1.4. That gives us a reasonable amount. You can see enough detail in stars to be like the visual impression of the sky, getting down to maybe magnitude 4 or 5. If you had a wider angle lens, you probably lose a bit on speed, and you're also going to be closer to the hubcap, so you obscure more of the sky. So there's a balance point in there, and balance all those things together. The other point there, with a reversed view, because it's a mirror, you can process your images, turn them around, so you can get a more natural view in orientation. The other factor can be dew. You've got a large metal surface there that in a cold night, that's a good collecting point for moisture. So mine, I've actually made a bit of a modification. Those two lugs are for banana plugs, and inside, just insulated with some urethane foam, but taped in there is some wire. That's the nichrome wire that generates a bit of heat with the current through it, and an insulator on it to stop it shorting on the hubcap itself. So the idea of that was to use a battery to pass a bit of current through it, calculated for the voltage ampage to produce enough watts to try and keep dew at bay for a bit longer. I tend to work with just setting it up to run for a couple of hours, so most times I can get away with that without using a battery with it. Where I'm running the thing at the moment, getting up on the shed roof, I don't also want to be lugging up a 12-volt battery there as well. Other thing here, I haven't tried it, but I know some members have been using the phone cameras to do basic wide field photography type shots. So there's a possibility to use that in a similar arrangement. A lot of phone cameras now have intervalometer or time-lapse type capability. So you could do a simple thing to monitor the whole night sky for a period of time with an existing phone camera, or your old phone camera even. So I'd like to see if anyone else has tried kind of wide-angle time-lapse type stuff with a phone camera, because if you had a number of members doing this sort of thing, we can create a very wide-angle photography members network or something, so we have data on covering the sky across all the peninsula. And then you could say on any given night, surely someone has managed to turn their rig on and managed to capture a freak event or aurora or something that happened. It wouldn't all be switched on at the same time, but someone would probably catch it. So that's using this sort of technology. It's an easy way to capture it without having to invest in a true all-sky camera. I think we now have one mounted on, it's either this shed or the other shed. So part of this could be we could tap into that data set as well. I was hoping Guido would be here tonight so I could have a chat to him about that. But that's something for the future, to make more effective use of the images we can collect and maybe do some possible science with them. Anyway, thanks for listening, and be inspired. And the last cartoon there is really just a play on the term fisheye lens. Righto. Okay, thanks. So I'll just briefly throw it to the floor. Anyone got any further questions? Yeah?
Yeah, I was wondering, so how high above your hubcap do you set your camera?
So it's probably 3/4 of a tripod's full extension. So if you've got like 3 steps on the legs, you're going 2 steps out and a bit. So it's probably less than a metre. And currently the rig I've built next to my shed, so you climb a ladder and get onto a platform, the walls of that extend enough and have a beam off over where the hubcap sits, so you just attach the camera to that at about that same distance. So now there's only one projecting arm, not 3 legs in the shot. So it's a little more convenient that way. I think one of the photos I had might have been done that way.
I think I saw it.
One of the earlier ones. Yeah, so that one on the right, so you can just see the thicker arm is the treated pine post, which is about 5 metres long up into the sky, and there's a thinner piece of timber going across with the camera attached to it. So there's no other legs in the shot, so you can see more sky, even though the only bit of interest was that tiny meteor way down there. Yeah.
I've got a 24-inch searchlight mirror, which is a very neat trick, is to melt lead with it.
Yeah.
But you could scrape the back off it and resilver it without a real fire, and that would make a rather effective background. It's got about focal length of about a foot, so it's sorry,
Yeah.
it's a 2-foot diameter mirror with a 1-foot focal length, but you can do it to the backside after.
Yeah, and because you've got the extra width, your proximity of your camera to that in this effect.
Yeah, you get the field.
Yeah, but you may find workarounds for that, but at least you're not going to obstruct too much of the image, even though you're a bit closer. Again, it's this began as a what-if experiment, and we're kind of going beyond and trying to see what else we can do with it. But because of the original idea of a hubcap is a readily available entity, and they make them with a decent chrome finish at very low cost, it's an ideal starting point.
What I guess I'm doing is I'm offering it to somebody who'd like to have a go at it.
Yeah, maybe.
I'm quite prepared to let them have it.
Yeah, maybe.
Even if they just don't want to melt lead with it.
Or do other experiments with it. Yeah. Well, I won't take it up at the moment. I've got what I need at the moment. But I'm sure if someone else is going to give it a go, yeah.
This talk is given by Professor Inna Sharf of the Department of Mechanical Engineering in Montreal at McGill University. And it's all about removal of space debris and the missions and science around it.
And today we're joined by Professor Inna Sharf from McGill's Department of Mechanical Engineering. You're welcome to ask questions anytime in the various stream chats throughout this talk, and we'll have a couple pauses, I think, where Professor Sharf will be able to answer questions as well as at the end. And so we're going to today hear about Professor Sharf's super exciting research on space debris capture and removal. And so with that, please take it away.
Okay, well, thank you very much for the introduction. Good evening, everyone. Thank you very much for inviting me to give this talk. I'm really happy to have this opportunity to tell you a bit about our research, and I want to thank everyone for joining in. So the first thing that I would like to do is actually acknowledge the work of the people in my research group who are really behind this work, and that's my amazing PhD students, Eleonora, Mikkel, Catherine, Tai Chow, Luke, Mikhail, and Pamela Wu, who was a research associate with me, and also a longtime colleague and collaborator, Professor Luna Misra from my department. So here's the overview of my presentation. I'm going to first give you some general background on space debris, and also introduce you to the concept of space debris removal and why we are looking at this problem. And then I'm going to focus on some of our work with a little bit of sprinkling of work of others. And I'll talk about active removal of large debris. I'll talk about mission for multiple debris removal. Then I'll talk about passive debris removal. And I'll end with sort of some of the more scientific aspects of our work related to understanding and predicting rotational motion of debris. All right, so a little bit of background. So what is in near Earth space? And for the most part, our work is confined to things in what we call the low Earth orbit, or LEO. So as many of you know, in the last 60 some years, we've been launching things into space, and we've launched more than 10,000 satellites, and most of them are still in orbit, but most of them are also not functional anymore. So approximately 2,300 are still operational systems. These numbers are a little rough, and of course they're changing continuously. Around 34,000 objects are larger than 10 centimeters in size. And I specifically mention this because these objects are trackable from the ground, so we can track them from instruments on Earth. And then we have something on the order of 1 trillion objects of size that's smaller than 5 centimeters. So what is space debris? Well, the space debris are comprised of things like, obviously, defunct satellites, so satellites we launched that are no longer operational, and upper stages. Upper stages are parts of rockets that are helpful for launching satellites, as shown in this picture that I have. Then we have things that are fragments from collisions. And these collisions can be collisions between satellites. For example, we had an accidental collision in 2009 between Iridium-33 and Cosmos 2251. And then sometimes we have intended collisions, as was the case with an anti-satellite test conducted by China in 2007, where they destroyed their own defunct satellite, Fengyan 1C. And then we have things that are fragments from explosions, as, for example, a battery explosion that happened on the NOAA-16 satellite in 2015. So all of these things contribute to space debris of all sizes. So why is space debris a problem? Why are we sort of concerned about this? Well, of course, space debris create increased space debris pollution. And what happens is, as objects collide in space, they will generate an increasing number of additional objects. And as those collide, and there's more debris. And this is what's called Kessler syndrome, named by Kessler in 1978. And so essentially you have this sort of exponential like growth of debris. And from a practical perspective, this creates a collision threat to operational spacecraft. And even an object as small as 1 centimeter in size can create substantial damage. Why? Because of relative speeds that things travel at in space. For example, speeds as high as 10 to 20 kilometers per second in LEO. So even a small object traveling at that kind of speed can pretty much take out a functional spacecraft. Now, so you take all of this in the context of where we are now, and we are now in the era of mega constellations. We have companies like SpaceX and OneWeb and others launching thousands of new satellites over the next decade. So you can see how this is becoming a concern. And so that brings me to the topic of active debris removal, or ADR. So currently, there's really general agreement on the need for active debris removal. And the big focus right now is on removing large debris. So these are objects that have the greatest probability of generating the highest amount of fragments in the future. So they tend to be massive objects like defunct satellites and spent rocket bodies like the upper stages that I was showing earlier. And there is currently sort of a consensus among researchers in this area that removal of 5 to 10 large objects from LEO, from the low Earth orbit, per year should stabilize the growth of space debris. So this is based on predictive models that we have for debris growth. All right, so we sort of think that we need to do active debris removal, and we think that we need to remove the larger, more massive objects first. And large space debris are difficult. So first of all, as I've said, this is, by definition, they tend to be pretty massive, which means that removing them gets to be expensive. So as an example of a debris, I have a picture on the right of NVSAT, and this is sort of, in my group, we call it the most desirable, the most sought after debris out there. So this is a spacecraft that's about 8 tons in mass, and it's the size of a school bus. And as you can see from this picture as well, many of these large space debris have complex geometries. They are made up of multiple segments. So you have the bus of the satellite, then you have the solar array, which is sort of off to the side, and then you have a large antenna as well. And that creates problems when you're trying to grab or capture one of these objects. Another issue is that these things tend to be tumbling because they're usually no longer under attitude control. And so they're sort of rotating in this, you know, kind of not very clear fashion. You can't identify a fixed spin axis of rotation, and they're literally tumbling. And another thing that makes it difficult is that they don't have special grapple fixtures. They don't have handles by which you could grab them when you're trying to capture them. So all of these sort of characteristics make large space debris difficult. So what would a typical active debris removal mission look like? Well, basically, you need to launch a removal spacecraft. And in this field, we usually call it chaser. They chase a spacecraft. Then that spacecraft has to rendezvous with the target debris. It might need to analyze the motion of the target debris, and then it's going to capture it in some way, stabilize sort of the whole system, depending on how the debris was captured. And then the whole system is deorbited with the chaser spacecraft, essentially firing engines to bring the whole system to Earth. So one of the things about ADR is that it's complex. It's a multi-stage process. There are many sort of elements in these missions. It's multifaceted, and to date, we have not had a real mission where a real debris has been removed, but we have had some demonstration missions. And I'll mention here specifically the Remove Debris mission that took place 2-3 years ago out of the University of Surrey. And currently there is a mission going on, which is called ELSA-D. And this mission was put up by Astroscale, which is a Japanese startup. So let me now say a few words about our research on ADR. And in my work and the work of my group, we've really focused on one of the parts of the mission, which is related to debris capture. And we've investigated two approaches for capture. One is what we call a robotic capture, and that's where the chaser, I'm not sure if you can see my mouse, but the chaser is equipped with a robotic arm, as shown in this picture, and the robotic arm literally grabs the debris to capture it. And the other is what we refer to as tethered net capture, and that's illustrated in this picture. And that's where we throw a tethered net towards the debris, and the net envelops the debris, and then you tug the debris to deorbit it. And I'm going to say a bit more about both of these approaches. So starting with the robotic capture of space debris. So again, sort of the idea here is you have a servicer, they chase a satellite. It's equipped with a robotic arm, as what's shown in this picture. This is a 7-degree freedom manipulator, and you are using the robotic arm to capture the space debris. So this in itself is also a multi-phase operation, and it includes things like approaching the debris, because you need to get close if you are going to grab it with the robotic arm, the actual sort of grabbing maneuver. Then if the debris, given that the debris is tumbling and you had to be moving the robotic arm to grab it, you need to sort of rigidize the whole system. And then you want to berth the chaser to the target to make them a single sort of body that you can then launch towards Earth. So for a number of years, we carried out work on sort of the approach and grabbing aspects of this by using a facility that I had in the lab, in the Aerospace Mechatronics lab. This is my lab here at McGill that I co-direct with Professor Meir Nahon. And we used the blimp, which you see here in red, to emulate a debris in space, right? Because the blimp is free floating, and then we had a robotic arm, and the robotic arm would essentially go towards the blimp and then try to grab it, as it just did here. And I'll show you here another video of the setup. We have another version of the blimp here in white, but it's basically the same idea. The robotic arm moves towards the blimp, grabs it by a little handle, and tries to sort of stabilize. Another thing that we did on the robotic capture was we worked on post-capture specifically of Envisat satellite, and this was done as part of a contract that I worked on with Professor Misra a few years ago, and this was a contract with Airbus DS. And so the two aspects that we worked on here was actually the immediate post-capture, where you want to rigidize the system and then berth the servicer to the target. And so this was really specifically oriented towards capturing Envisat. And again, just to remind you, it's an 8-ton spacecraft, very large in size. It was declared to be a debris in 2012, and it's tracked by observatories worldwide, which will be relevant to the later part of my talk. So in this work, we used the dynamic simulation to basically study the system rigidization. That's after you've captured Envisat, which is tumbling, and you're trying to make the whole system rigid. And then you want to use the robotic arm to bring the chaser, which is this kind of goldenish body, to berth, to dock to the launch adapter of Envisat, because once they're docked together and they're firmly sort of put together, then you can fire the thrusters on the chaser and launch the whole system towards Earth. So this is a movie. You see 4 panels. It's the same thing, just sort of 4 different views. Again, this was done with the dynamic simulator. And what you're going to see here is the berthing of the chaser to the launch adapter of Envisat. And the things to sort of maybe appreciate here is that you have to do this without colliding, having anything collide. You don't want any collisions of the robotic arm with any parts of the debris. You don't want the chaser to collide with anything, right? You want this done smoothly. It has to be done accurately. Airbus at the time also gave us time constraints on this particular maneuver. They wanted it done, I believe, within about a minute. And all of this has to be done, of course, within the constraints of the actuators of the robotic arm. So that was a really fun project, and we got to go to Germany to present it to Airbus at the time, and it was really an exciting project to participate in. All right, so now I'll talk about the net capture of space debris. So this is our second approach that we investigated in my group. And this approach was and is still considered a very sort of strong contender to the robotic capture for several reasons, and it has a number of benefits. For one, it's a very scalable approach. If you make a large enough net, then you can capture the debris of several different sizes. Another kind of nice feature about it is that you don't have, there's no collision risk between the chaser and the debris target during the capture, because you can actually maintain a pretty substantial distance, like 50 meters, between the chaser and the target, since you're launching the net towards the debris. And this is very different from what we saw in the robotic capture, where the chaser has to be pretty close to the debris, which of course, makes it more difficult. And another benefit of the net capture is that it's better for capture of tumbling debris. So even if the debris is tumbling, you don't sort of need to worry about it so much, because you're just kind of throwing literally a fishing net over it. And the fact that it's tumbling is not so much a concern. So how does this work? Well, basically, you initially have the net in a canister on the chaser, and then the net gets ejected out of this canister with corner masses. So at the corners of the net, you have kind of masses which get ejected through some sort of a mechanism, and those masses then sort of pull the net with them. And you entangle the debris, sort of contain the debris inside the net, and then you tug this sort of system to the disposal orbit with your chaser. So that's the basic idea. Now, as with anything we do in space, we want to be able to have simulation tools, reliable simulation tools, so that we can use them to plan the mission, to do the analysis, to investigate our different options, see how different parameters of the system might affect the success of the mission. And so when we started to work on the tethered net capture, there was actually little prior work on dynamics modeling and simulation of these systems. And so we embarked on developing such models and tools. And I thought I'd show you sort of a progression of our models. So when we started, our nets were very simple, and we had really very sort of primitive simulations of them. And then we graduated to more sophisticated models. Our nets got bigger. Our model of the net got more sophisticated, more accurate. Then we included in our simulations a debris. Here, the debris is just a box, a very sort of simple piece of debris. But this is a very big step when developing a simulation, because now we have to model the contact, all the contact dynamics between the net and the debris. And then we progressed further with this. We made our debris look more realistic. This is actually modeled after one of the upper stages. We made the debris rotate. And at this point, we had some interesting insights from our simulations. So initially, we sort of thought, well, the net is going to go around the debris and it's just kind of going to sort of stay containing the debris. But as you will see in this video, after a while, the net opens up and flies away from the debris. So needless to say, that wasn't going to be very successful capture mission. And so finally, here's another movie illustrating the progression of our modeling and simulation tools. So now we include the chaser, which is this little box up at the top, and then there's a tether, right? This is a tethered net. And then we also included a closing mechanism to ensure that the net stays around the debris. All right, so I'll now sort of switch gears a little bit, and I'll talk a little bit about the multiple space debris removal work and mission that we researched. So the motivation for this was the fact that, as I mentioned earlier, there's a general consensus that removing 5 or more large debris per year would stabilize the debris environment in LEO. And so we embarked on this work with the objective to investigate the feasibility and optimization of a multiple space debris removal mission. And so really, we wanted to develop some tools that would allow us to figure out, is this actually feasible? Can we remove 5 large debris in a year? How expensive would it be in terms of fuel requirements? And so we developed a time-optimal control formulation for doing a recursive removal mission scenario. And so let me explain to you what I mean by this. So this is a figure showing, Earth at the center in blue. Then we have an orbit in green from which our chaser, which is a blue diamond, would sort of start. And then in this figure, I have 3 debris, each in their own orbit. And the idea for a recursive removal mission is that the chaser would travel to debris 1, capture it in whichever way, robotically or using tethered nets or using something else, and then bring it down back to a very low orbit, release it. From that orbit, the debris would deorbit naturally very quickly. And then the chaser would move to the second debris, right, to the second debris orbit, capture that, bring it down release it, and move then to the third debris orbit. And so this is sort of a recursive mission where the chaser goes to one debris, brings it down, back up, and down. Now, so we wanted to look at optimizing this mission from the perspective of minimizing the time that it would take, but of course, the fuel requirements for a mission like this is also a big concern. So in formulating this problem, we early on realized that we needed to look at a chaser that would have low continuous thrust capabilities, so thrusters that would produce not a lot of thrust, but continuously. And we also realized that RAN differences between orbits, and I'll define RAN in a second, make the mission quite expensive. It requires a lot of fuel to do orbital transfers between orbits which have very large RAN differences. Now, what is RAN? RAN stands for right ascension of the ascending node. That's basically an angle between, it's an angle measured in the equatorial plane between the vernal equinox and the intersection between the orbit and the equatorial plane. So the important thing here is that the drift orbit would allow the chaser to reduce the RAN difference by while the chaser would be drifting for some time in the drift orbit under natural RAN drift. All right, so what are some of the special considerations for such a mission? Well, one of them is debris selection. How do you select the debris that you're going to go after? And the things that you want to consider here are the risk factors of the debris and their orbit, because that ultimately impacts the cost of the mission. Once you've selected your debris, then there's a question of how are you going to sequence, in which order you're going to remove the debris. And again, the considerations here are the cost of the transfers between the different orbits, achievable RAN changes, and how much that would cost in fuel. And so we developed a methodology to solve the time optimal control problem. And then we applied this methodology to sort of different sets of debris. And I wanted to show you an example here of a set of 5 debris, which included Daiichi. Daiichi was a Japanese spacecraft, Envisat that I already talked about, and then 3 sort of upper stages as well. And if you look at the last column, which shows the mass, you can see that these are pretty massive objects, 4,000 kilograms, 8,000, 9,000, etc. And also this table presents the orbit. So the standard orbital parameters that are of concern here are the semi-major axis, A in kilometers. That's basically the radius of the circular orbit. And then we have the inclination in the second column, I in degrees, and then the RAN. And you can see that there are substantial RAN differences between some of the debris in this particular set. And so the outcome of the solution is basically a detailed mission plan as summarized in this table. I'm not going to go through all these numbers, obviously, but basically the mission plan would tell us, okay, you're going to move to a drift orbit located at this semi-major axis, then you're going to travel to the first debris, and as part of the solution, you get all the detailed information, how much time different parts of the mission would take, how much fuel you're going to need, how long you're going to spend in different drift orbits. So the important columns here are actually the last 2 columns, which show the time spent in different parts of the mission and the fuel cost. And at the bottom, we can see that the mission total for this particular set of debris was about 814 days, which is actually more than 2 years. And the fuel cost was about 2,800 kilograms, which is also quite substantial. But this is just to illustrate, what kind of information we can get from this time optimal control solution. All right, maybe I'll take a few minutes if there are any questions before I continue.
related to concerns about how expensive it is to get mass into orbit in the first place, and wondering if there's any way to recycle objects that are, debris, rather than just deorbiting and destroying them.
Right. Okay. So it is expensive, and that's actually one of the points I was going to make right here. Active debris removal is very costly. You're launching a spacecraft to get the debris, and then and you're basically going to, it's a kamikaze mission, right? Both the spacecraft, the chaser, and the debris are just come crashing to Earth. There is a lot of work, or quite a bit of work that's happening right now on what's called on-orbit servicing. And this is an area that's a little bit complementary to space debris removal, because some of the problems are very similar. So the idea behind on-orbit servicing is that, okay, you have a defunct spacecraft. Very often the spacecraft becomes defunct because it simply ran out of fuel to do the orbit maintenance. And so why not, refuel these spacecraft? So that's one possibility. Sometimes we send a spacecraft and something malfunctions very early on in the mission. And sometimes it's actually very simple malfunction that could be easily repairable if you sent another spacecraft. Then there are people that are very much looking at recycling ideas. So if we have this defunct spacecraft and this other piece of defunct spacecraft, can we kind of recycle these things and put another spacecraft from these pieces in orbit? So there are people working on these. There are various concepts. We are still quite a ways from, sort of having these concepts become a reality, but it's definitely something that people are working on.
That's great to hear. I think we had another question. For your net mechanism that you were talking about, someone wanted to know, how does it close? How does that closing mechanism work?
Right. So here again, there is sort of several ideas that people have proposed. We came up with an idea which resembles a little bit, if you have a sleeping bag and you pack it into like a little sack and you just kind of pull on the string to close it up. So the idea that we had was, why not take our main tether and sort of extend it out along the perimeter of the net. And then once the net is sort of around the debris, we were going to pull on the tether to close it. So that was one of the ideas that we worked on it, and we tested it in simulation, and it worked pretty well. So, but there are also other concepts for closing the net.
Cool. Maybe we can just do one more short one. I think one person wanted to know, there was a previous slide where you mentioned that maybe like 5 big space debris removals per year would be sufficient for, I guess, stabilizing low Earth orbit. They were wondering how many years total would be needed for that, like 5 per year for how many years?
So the idea here is that, based on the prediction tools that we have at our disposal for sort of predicting the debris environment and the evolution of the debris environment, the 5 to 10 debris per year number is agreed on as something that will stabilize the environment. In other words, it will stabilize the growth of the debris. So there won't be, the number of debris will not grow, but will kind of more or less stay constant and maybe even decrease a little bit. So it's something that we would need to continue doing, I guess, ad infinitum, for as long as and of course these numbers are based on predictions of how many things we're going to be launching into space. But for now, over I'd say the foreseeable 10, 20, 30 years, that's kind of the number that people have in mind. Yeah.
Like a continued maintenance sort of.
Yes, exactly. Yeah.
Awesome. Well, I think that's probably enough questions for now. So
So this brings me sort of to the next topic, which is passive debris removal. And as we were just saying, active debris removal is expensive. And so researchers have been looking into other ways to speed up really the deorbitation of debris, because that's what this is really about. And one strategy that received quite a bit of interest utilizes the effect created by coupling between two orbital perturbations. And this is called SRPJ2 coupling and resonance. SRP here stands for solar radiation pressure, and this is one of the perturbations, one of the forces and torques that's exerted on objects in space. And J2 represents the gravitational effect due to the fact that Earth is not spherical. Earth is not a perfect sphere. It's kind of a squished spheroid. So these two perturbations, when they couple, may create what's called a resonant effect. And this phenomenon has actually been known, and theory for a long time, and theory for this was put forward back in 1933. But what happens when you have these two perturbations couple is that this can lead to a significant increase in orbit eccentricity. Now, so what does that mean? Well, so I have a little figure here. You have Earth, then you have orbit, and then you have perigee, which is the closest point in the orbit to Earth. And increasing eccentricity means that as the orbit becomes less circular, so it becomes more elliptical, as this happens, the perigee, which is the closest point in orbit, gets closer and closer to Earth. So by increasing eccentricity, you end up lowering the perigee to an altitude where the atmospheric drag becomes significant enough that you can then accelerate the time to deorbit. So that's sort of the basic idea for this phenomenon. So there's been quite a bit of interest in this over the last several years, and there was a Redshift project, which was a European consortium of researchers, and as part of this project, so first of all, this project was motivated by basically the need to minimize environmental impact of mega constellations, given that that's what's happening over the next decade. And essentially, researchers under this project created literally a cartography of resonant orbits in LEO. Now, the thing about this SRPJ2 resonance is that it only happens in very few and specific orbits. So, for example, so this is an example of a resonant orbit. It has a semi-major axis of about 8,000 kilometers. It has a particular inclination of 39.5 degrees and initial eccentricity of 0.03. So when we started looking at this, one of the first things that we actually wanted to do is validate, this effect in simulation. And so I have a graph here that shows the eccentricity as a function of time, and this was done over 10 years. And this is a result from an orbital propagator that we developed, which I'll talk about a little bit later again. And these curves were obtained by varying the inclination slightly away from the resonant orbit. So the resonant orbit is at 39.5, and we tested this for inclinations ranging from 38.5 to 40.5. So fairly small deviations in inclination. And so what you can see here is that the yellow line, which corresponds exactly to the resonant orbit, you can see that the eccentricity is increasing, right? And it's just increasing over the 10-year time frame. While for the orbits that are near the resonant orbit, you don't see this phenomenon. So indeed, this is a real, or this is a phenomenon that we can definitely reproduce in simulation. And so again, as the eccentricity increases, you bring the perigee closer to Earth until you get into the enough atmosphere to slow down the debris and to bring it deorbited naturally. All right, so in my group, we've undertaken to look for the SRPJ2 coupling or resonance among all objects for which observations are available. And this is actually work that's ongoing. One of my PhD students, Catherine Massey, is working on this. So I wanted to illustrate this with an example of a spacecraft. This is a spacecraft called Echo 1. It was a NASA spacecraft that lived in 1960s for about, it was in orbit for about 6-7 years. And this is one of the spacecraft for which the SRPJ2 coupling is actually very prominent because of the high area to mass ratio. This is, the spacecraft was actually a balloon, so it had a very large area, but was fairly light. So what I'm showing in the figure here that I've just put up, first of all, there's two plots. The top is the semi-major axis over time, and the bottom one is the eccentricity. And in each figure, I have sort of three curves. The black is the observations, and the observations for things in orbit come from TLEs. These are two-line elements which give us all the orbital elements of an orbit. So the black dots are basically measurements, and then the blue and the orange are what we compute with our simulations, with our orbital propagators. And the orange one is without the SRP perturbation in the orbital propagator, and the blue one is including the SRP perturbation. So therefore, the SRPJ2 coupling is in effect. And so you can see that the eccentricity definitely increased quite a bit. So it sort of oscillates, which is one of the reasons people call this a resonance. And because of this SRPJ2 coupling, the spacecraft came down to Earth much faster than if this coupling didn't exist, right? So remember, the orange line shows no SRP, while the blue line shows SRP included. And you can see that it descended to Earth quite a bit faster. So we're actually we are reviewing databases and TLEs for about 50,000 objects in space with a view to finding this phenomenon in real objects in space. Another part of our work on the passive debris removal has had to do with the idea of looking for another type of resonance. And we've called this the SRPJ2-phi resonance. And this is essentially a new type of resonance that also leads to substantial increase in eccentricity. And the way it works is by imposing a particular spin state on plate-like spacecraft. So remember, one of the things I mentioned for the SRPJ2 resonance, this happens in very few specific orbits. Now, your debris might not be necessarily in a resonant orbit, but by making the debris spin, giving it a particular spin state, we can induce this new SRPJ2-phi resonance. Now, you might think, well, okay, you're proposing this for plate-like spacecraft. Are there plate-like spacecraft? Well, as a matter of fact, if you look at Starlink, which is a spacecraft from SpaceX, that's part of the SpaceX's mega constellation, most of the spacecraft is actually the solar array, and that's a flat plate, and it's only a small part of the spacecraft that's the body. So again, to sort of give you an illustration of this, here I'm showing propagation results for plate-like debris modeled after the solar panel of Starlink. We've put it in sort of a realistic orbit. And again, I'm showing here the semi-major axis as a function of time and the eccentricity, comparing spinning in blue and not spinning. And you can see that the SRPJ2-phi resonance is in effect. The eccentricity does increase, and we are able to deorbit, bring to Earth the spinning spacecraft quite a bit faster than had it been not spinning. All right, so this brings me to sort of the last topic that I wanted to cover today, and that falls under the subheading of science. So we talked about the issues arising from the rotational motion of debris, right? We said that while debris tend to tumble in space, and if you want to do active debris removal, then you're going to have to grab something that tumbles. And if you want to do this with a robotic arm, well, that's not so easy. So if we are going to be planning ADR missions, then we thought that it was important to have models and simulation tools that would allow us to predict rotational motion of debris for many years, right? Because if you're planning an ADR mission for, I don't know, 2028, you want to know how is your object going to be tumbling when you send that mission, right? So that you can be properly prepared to accommodate this. So we initially, when we started looking at this, we were very much motivated by the ADR application. But then as we sort of did more research and looked at the literature on the subject, we actually discovered some fascinating facts and mysteries, and this work ended up sort of taking a life of its own. And in particular, we became very interested in accurate modeling rotational motion over long term, so over, decades. And we wanted to compare our models to observations. And another thing that we were interested in, we wanted to have a clear idea of how the rotational motion affects the orbital motion. And this is important for orbital predictions and re-entry analysis. So what are these mysteries and sort of fascinating facts that I mentioned earlier that we came across? Well, one of the mysteries was actually the Envisat spacecraft. And this is why the title of the slide is the Envisat Enigma. So one of the things that we found out was people observed, or researchers observed, a substantial spin-up of Envisat that happened shortly after it was declared defunct. So what I'm showing here is the plot of the angular velocity of Envisat over time. This vertical dashed line is the time when ESA said, okay, the spacecraft is defunct. And the little crosses here are observations that were collected of the rotational motion of Envisat. And you can see that shortly before it became defunct, it was rotating fairly slowly. And then you see this increase, right? The little pluses are going up to about 3 degrees per second. And to this date, nobody actually knows what caused this, the spin up. After the spacecraft became defunct, many observatories around the world sort of got in and started taking observations of the rotational motion, and it shows that the spacecraft is slowing down. And as you can see, there's actually quite a bit of agreement between the different observational campaigns. So there's several observational campaigns here from different groups, and there is in general an agreement. So that was good. But the other part of the enigma was that even though there was quite a bit of agreement on the rotational speed of Envisat, there was actually a lot of disagreement and sometimes even contradictions on the orientation and the motion of the spin axis of Envisat. So I wanted to show you this graphic here that I have at the bottom right. So first of all, this is not to any particular scale. This is really just to illustrate things. So I have Earth in blue. Then I have the orbital plane of Envisat. All right, so the orbit is sort of this, the circumference of this reddish graphic. And at the bottom, I have the little schematic of the spacecraft itself, right? This is ENVISAT itself. And then what I've shown here is the angular velocity vector, omega. This is the axis of rotation of ENVISAT. And so what we found was that there was actually quite a bit of disagreement on how that axis of rotation is oriented and how that axis of rotation moves with time. So to give you some examples of the conclusions drawn from different observation campaigns, some people were saying that, well, the axis of rotation is oriented 28 degrees from the orbit normal, from the normal to the orbit, and it nutates with the orbital period. Then some observational campaigns were saying, well, no, actually we think the axis of rotation is fixed, and it's fixed at 17 degrees from orbital normal. And then other observational campaigns were finding very large spread in spin axis. So we were really pretty sort of fascinated by all of this, and that motivated us to work on developing models and looking very closely at the rotational motion of space debris. So in this work, which was a big part of the PhD student Luke's year, we developed a comprehensive model of the rotational motion and an orbit attitude propagator, DSPOS, called DSPOS. We validated DSPOS against observations of rotational motion, and we employed DSPOS to investigate the rotational motion of ENVISAT specifically, as well as some other spacecraft. And we were trying to shed some light on what ENVISAT's rotational axis was actually doing. So I'll say a couple of words about DSPOS itself. It's a state-of-the-art orbital attitude propagator. And it includes a number of perturbations that are not commonly modeled. And they are the gravity gradient torque, the aerodynamic torque, the eddy current torque, the radiation torques, which come from direct solar radiation. This is the SRP that I was talking about earlier. Then you have the albedo effect, and then you have the infrared radiation from Earth. It also includes internal energy dissipation and hypervelocity impacts. So these are all effects that are perturbing the rotational motion of the debris from what we would normally call a torque-free motion. So all of these effects are modeled and disposed to probably the highest degree of accuracy available. So in this slide, I wanted to show you some of our validation work. So you have this powerful modeling tool. We're able to simulate the rotational motion of debris over long periods of time. We wanted to see if we can validate it against some of the observations. And to do that, we used spherical geodetic satellites, for which there was a lot of observational data available. And one of the reasons for it is because these satellites are equipped with retroreflectors. And so it was very easy to observe their rotational, it's fairly easy to observe their rotational motion. So what I have shown here are three sort of figures. The first one on the left is showing the period, which is inversely related to the spin rate. And then the other two figures show the declination and the right ascension. So this basically gives you the orientation of the axis of rotation, right? So it gives you information on how the axis of rotation is oriented in inertial space. And in each figure, we have the black line, which is simulation with DSPOS. So this is the results from our simulations. And then we have two observations. We have, so these are from two sort of sources of observations. We have the light curves in orange dots and the SLR, which is the space. This is a laser ranging system in blue. And what you can see is that there is actually pretty good agreement between our simulation in black and the observational data. So that gave us a lot of confidence in our models and in our simulation tool. And with that information, we then were able to really investigate the rotational motion in Ben Bisset. And so at this point, we hypothesize that Bisset's rotational motion has 3 distinct motions. And I say that we're hypothesizing on this because until we have enough observations to confirm this hypothesis, it remains a hypothesis. So basically, we think there are 3 distinct motions that contribute to rotational motion of Bisset. The first one is the precession of the angular momentum with the orbital plane. So remember, I introduced to you the angular velocity vector, which is shown here kind of in this dark pink. Any rotating body also has an angular momentum, which is called h, and it's shown here in sort of this bluish, purplish color. So as the orbit precesses, so the orbital plane rotates about the Earth's rotational axis, the angular momentum is precessing as well. So that's the first contributor to the rotational motion. Then we have the nutation and libration of the angular momentum around the orbital normal. So that's illustrated by these 2 cones. So basically, the angular momentum vector is nutating about the normal to the orbit. So the orbit normal is shown here in this red vector n. And essentially, the angular momentum is doing sort of traveling along a cone around that orbit. That's called nutation. But in addition, that cone itself is sort of librating. And the limits of the librational motion are shown by the blue cone and the yellow cone. And the third part of the motion of the angular velocity vector is the angular velocity vector is actually wobbling around the angular momentum. So omega, this pink, dark pink vector, is itself sort of wobbling around h. And remember that the spacecraft itself is rotating about omega, right? So these are these are contributions, the main contributions to the angular velocity, to the motion of the angular velocity vector. And that's sort of our current understanding of the rotational motion of Bisset. All right, so with that, I'm going to conclude my talk. So as far as space debris goes, I think this will likely become a bigger problem in the coming decade because of the launch of mega constellations. I think that active debris removal is actually reaching a pretty high technology readiness level. We've had some successful demonstration missions, but nevertheless, it's an expensive mission. And at this point, I'm not really sure when a real mission will take place. So there's really no certainty on when that might happen. The passive strategies that I talked a little bit about by exploiting this sort of SRPG2 resonance and possibly the new resonance that we proposed. At this point, I'd say the word is still out on whether this is going to be at all a practical solution, and this requires more work. And the last thing that I want to mention is that rotational motion of large space debris is complex. I think it's fascinating. Researchers are still working on understanding it, modeling it, and modeling how it affects the orbital motion. And I think that brings me to the end.
The NBISAT rotational motion is just, I can't even hold all of that and visualize it. So props to you guys for trying to figure out all those components. So I think we have many more questions, and I'm just going to try and pick a couple to start with, and we can go from there. So someone had a question about, for this passive removal, the like resonances you talked about, is there like a particular like rotation rate or like range of rotations that you need to achieve that resonance?
Yeah. So yes, so there would be a particular rate. It would depend on the orbit that the object is in, and we're finding that it's a very slow rate, and essentially it has to do with you sort of are trying to maximize the SRP effect, the solar radiation pressure effect, and so you want to be sort of pointing your plate-like spacecraft as much towards the sun. So it's a very slow rate, and you need to do some work. You need to have some mechanism to get your debris to maintain that rotational motion. This is why I'm saying it's not at all clear whether this is going to be a practical solution. So yes, so definitely we know how to compute that rate.
Great. Another question, someone wanted to know, actually a couple people were wondering, sort of like what are the main methods we use for detecting debris in the first place? I think you mentioned like observations from observatories.
Yeah, so our main method is we can observe anything that's larger than 10 centimeters, we're tracking from the ground. So that's happening continuously, right? And that information gets published every few hours. TLEs, the tune line elements, which is basically information on the location of the debris in orbit, gets updated. So that's what we do. For things that are smaller than 10 centimeters, we're out of luck. And this is one of the reasons this is sort of an issue, because as I've mentioned, even something as small as, you know, an object that's about 1 centimeter in size can create substantial damage. So we observe debris from Earth, and that information, of course, is available to satellite operators.
Are there like just particular telescopes that are sort of constantly monitoring, or is it sort of like on and off thing?
I don't think I can tell you exactly, because I'm not sort of so much, I'm not really that involved on the side of things. Mm-hmm. For us, we get these TLEs and we're happy. Yeah, I don't know if Catherine is on the call. Maybe she'd be able to answer this question.
I'll keep an eye on the chat and see if we get another response. I was just curious because I'm on the astronomy side, so I'm like, huh. Yeah. Very cool.
Yeah. So there is what is it called? The Space Surveillance Network. There's a couple of, you know, large networks. One is the US based and the other one is Europe based. And that's where these observations are sort of actually happening and information gets published.
Very cool. I think we also had a really good question. Oh, yes. So I guess this is sort of maybe like a comment / question, but someone mentioned that basically shouldn't space agencies impose requirements on space programs to like build in a deorbiting feature rather than having to go back later and fix it? So is this something that's being discussed?
Absolutely. So this is actually happening. There are guidelines that exist, international guidelines that exist, that speculate that all things that we launch into space must come down to Earth within 25 years. Mm. The issue is that they're guidelines, so they're not laws, they're not necessarily enforceable. Some countries, I can't remember now, I think France might be one of them, actually have made it a legal requirement. But for as long as they remain guidelines, you know, that are not enforceable, it's not necessarily something that happens. Because ultimately, you know, people that launch spacecraft, for example, if you launch a communications spacecraft, you want to get as much life out of it as possible. To meet these guidelines would require you to have some fuel remaining to get your spacecraft back down, you know, so that you can meet this 25-year limitation. And an operator that's operating communication satellite that's wanting it to be functional for as long as possible is not necessarily wanting to, cut the mission life short, have enough fuel to meet this guideline. So that's sort of the current status to the best of my knowledge.
Tricky.
Yeah. Yeah. There is politics involved in this as well. Yeah.
Let's see, other questions. I think we just had a question from Susan. Who's paying for these missions? And I feel like this might also have some politics in it as well for the debris capture.
Yeah, so that's another question. And again, there's sort of discussion on this. So for example, with NVSat, it was an ESA-launched spacecraft. And so they're the most concerned about it. And one can make an argument, well, whoever launched the spacecraft, they should be responsible for a mission to remove it. To date, we haven't had a real mission, right? We haven't had a real mission. The demonstration missions are funded by, for the most part, government funding, to the best of my knowledge. So I mentioned two of them: remove debris, which was a mission from the University of Surrey. I'm pretty sure that well, in fact, I know that they've gotten funding through Horizon 2020, which is a European funding umbrella. And Astroscale's mission, I imagine, is funded from whoever is funding the startup. So the purpose of the demonstration missions is to demonstrate that, look, we think we have the technology to do this, or maybe not, and some more technology needs to be developed. And of course, a company like Astroscale, which is a startup company, they're hoping that eventually, if they demonstrate that they have the technology to do this, then somebody will give them the money to do the real debris removal mission. But who that somebody will be, I guess, will depend on which debris moved.
Which country does it belong to? Yeah.
Yeah.
And I guess we have one more sort of tricky politics-based question. Someone was wondering about, so I guess satellites can have sort of relations to the military, and has debris capture have you guys been thinking at all about like a scenario where you have someone that destroys satellites on purpose as like a military act, and how to deal with that, I guess?
Well, so in fact, China did this in 2007, right? They conducted an anti-missile test, and they destroyed one of their defunct spacecraft, and that created a lot of debris. Again, I don't sort of know what is the current legal framework for acts like this. So yeah, I don't really think I can say much more than that.
Might be another tricky scenario.
Yeah.
Let's see. I feel like maybe we have time for maybe a couple more questions. Let's see. Oh, okay. We just had a question in the chat from someone asking about, I guess, like, what are the sort of overarching guidelines or laws on, I guess, maybe like space-related debris capture?
So I'm not aware of any laws on the debris capture itself. Yeah, I'm not aware of any laws on debris capture at this point.
Okay.
But again, there are, definitely there are people involved in space law, and debris-related issues would be a subset of that area. We have some good people working on these in these areas at McGill.
Oh, cool.
But I'm really not the best person to give you answers on this.
yeah, maybe someone in like in space. I didn't even really know there was a space law.
Oh yeah, very much so. Very much so. Yeah.
Okay, and I think maybe we have a fun question. Someone wanted to know, is space debris big enough to see? And I guess so that would mean like with your eye, maybe like from Earth or.
I don't think so. So not, I mean, an object that's very large. So the larger objects, right, like objects that I mentioned, and this is probably one of the larger pieces that's out there. I don't think it's visible from Earth with the naked eye. I'm pretty sure it's not.
Yeah.
Space station, which is very large, and it's in a substantially lower orbit. It's somewhere around 300 kilometers. I believe that you can see it sometimes. You sort of see a dot in the sky, but it's just gonna look like a dot to the naked eye.
That's awesome. I think you can see like iridium satellites, maybe. I don't know. I feel like I've seen something about that. There's certain satellites that are very reflective, but not like the debris, just like actual satellites.
Right. Okay. Maybe.
I guess I think we've gotten to most of our questions, so that looks pretty good. I had one that I can ask that I thought of while you were talking. I was curious what happens if a capture fails or like messes up. Do you have a way to like retry, or is there a risk of like a cascade or something worse happening?
Well, so that's another thing that people are thinking about as they're looking at these debris removal technologies. So, imagine you're trying to capture using a robotic arm. So if you miss, can you try again? Well, possibly, if you don't, as long as you don't hit something and damage the arm, you could kind of maybe back up a little. So definitely there are some options. With a tethered net scenario, you can have a backup option where you carry more than one tethered net. So you've launched one, you missed. Well, you launch another one. The good thing about tethered nets is that they're very light, so you can easily carry spares. So yeah, I think it would depend very much on the exact technology that you're using to do the capture.
I see. I like the net. The net idea sounds good. Well, yeah, I feel like we've already taken up quite a bit of your time. So thank you so much for answering all these questions. And yeah, just learned a ton. And we've had a lot of comments in the chat saying thank you. So really, really great topic.
Thanks everybody for joining, and I hope you enjoyed the talk.
And we'll close with a look at the all of the moon phases and librations for all of 2025, set to music by Infraction called Deep Night. Goes for about 2 minutes, and we'll close. And before I press go, this is just showing some of the features that you're about to see. On the top left-hand side, you see the view from above of the moon's orbit around the Earth, and you'll notice the sort of the turquoise colour is the range of motion of the moon. So the moon is actually a slightly elliptical shape, but over time it sort of sweeps out that circular looking band as it goes around, and it shows the apogee and the perigee as it goes around the Earth. Down the bottom left is you get to see the libration and the wobble in the orbit over time. In the middle, you can see where the terminator is, the dividing point between night and day. And the horizontal line on the left-hand side of it, you see the blue Earth to scale. On the right-hand side, you see where the moon is to scale. And as you can see, it's about 30 odd Earth diameters away. So you just don't appreciate actually that the moon really is that far away. And you can see it move in and out as after I press go. Down in the bottom right-hand side, you see the date is actually shown there, and it will step through all of 2025, and it indicates the diameter of the moon in the sky and the apparent distance, and also the right ascension and declination of it if you were trying to look for it. And this is all from the Lunar Reconnaissance Orbiter. And that's the southern hemisphere view, so that has the South Pole pointing upwards in that diagram. And with that, thank you for coming to the meeting and staying. It's been a long one tonight, and we'll see you with the February meeting. Thank you.